Hello and welcome back. I'm so glad you're here. Tonight we're going to take a journey together, a slow, gentle drift through everything we know about Mars, the red planet, that rusty dot in the night sky that's been watching over humanity since before we had words for what planets even were. Maybe you had a long day. Maybe your mind is still buzzing with all the things you need to remember tomorrow. That's okay. You don't need to hold on to every single thing we talk about tonight. Just let the ideas wash over you like waves on a shore. Some will stick, others will drift away. Both are perfectly fine. If you're enjoying these cosmic journeys we take together, a like or a subscribe helps these videos find other people who need them, other restless minds looking for something gentle to focus on as they drift off. And if you have thoughts about where we should travel next, other planets, distant stars, the quiet spaces between galaxies, leave a comment. I read them all. But for now, let the day go. Let tomorrow wait. We have 100 stories to tell about Mars, and we're in no rush at all. Now let's begin. There's something about the color red that has always meant something to humans. Danger, perhaps, passion, blood. And there in the night sky, hanging among the steady white points of starlight, was a planet that glowed the color of rust, the color of dried blood on ancient battlefields. The Romans called it Mars, after their god of war. Not their primary god, Jupiter held that title, but the god who represented conflict, protection, and that fierce energy that courses through soldiers before battle. The Greeks had called it Ares. The Babylonians named it Nergal, after their deity of war and plague. Cultures separated by oceans and centuries all looked up at that same rusty point of light and felt something similar, something fierce, something that reminded them of struggle and survival. It's interesting, isn't it, that we named it after war, and now we dream of it as a place of peace, a second home, a refuge, a backup plan for humanity. Maybe that says something about us. Maybe we're always trying to transform the things we fear into the things we hope for. The name stuck. And now, thousands of years later, when we say Mars, everyone knows exactly which world we mean. That red one, the one that looks like it's watching us. So why is Mars red? It's a simple question with a beautiful answer. The entire planet is rusting. Iron oxide covers the Martian surface, the same compound that forms when you leave a bicycle out in the rain or when an old car slowly surrenders to time in a field somewhere. Mars is covered, from pole to pole, in a fine dust of rust. It's in the rocks. It's in the soil. It's suspended in the atmosphere, giving even the sky that butterscotch tint. Imagine that. An entire world, roughly half the diameter of Earth, oxidizing, slowly combining with oxygen over billions of years, transforming its surface into a planet-sized piece of forgotten metal left out in the cosmic elements. But here's what makes it even more poetic. Rust requires oxygen, and oxygen in large quantities usually means life, because life produces oxygen as a byproduct. Earth's atmosphere wasn't always oxygen-rich. For billions of years, our planet's air was toxic, filled with methane and carbon dioxide. Then photosynthetic organisms evolved, and slowly, over eons, they transformed our atmosphere, filling it with the waste product of their biology, oxygen. Did something similar happen on Mars? We don't know yet. Maybe that rust is just the result of chemical processes, water and minerals interacting over geological time. Or maybe, just maybe, that rust is a fossil, the last evidence of an atmosphere that once teemed with microscopic life, long since vanished. Either way, Mars rusts on, patiently, quietly, turning redder with each passing millennium. Here's a strange coincidence that feels almost too perfect to be true. A day on Mars lasts 24 hours and 37 minutes. 24 hours and 37 minutes. Not 18 hours, not 40 hours, just barely longer than an Earth day. A difference so small you'd adjust to it within a week, maybe less. Your circadian rhythm, that internal clock that tells you when to sleep, when to wake, when to feel hungry, is tuned to roughly a 24-hour cycle. Scientists have studied people in caves, isolated from sunlight and clocks, and found that humans naturally drift toward a sleep-wake cycle that's around 24.2 hours. On Mars, you'd be living almost exactly in sync with your body's preferred rhythm. Think about what that means for future astronauts, future colonists. They won't need to completely rewire their biology. They won't experience the disorienting jet lag that comes from living on a world that spins too fast or too slow. They'll wake up when Mars wakes up. They'll sleep when Mars sleeps. It's a small thing, perhaps. In the grand scope of planetary science, a day length is just a number. But for the humans who might one day call Mars home, it's the difference between feeling like you're on an alien world and feeling like you're somewhere that almost feels like home. The sun will rise in the east. It will set in the west. A day will feel like a day. And maybe after a long shift working in greenhouses or repairing solar panels, they'll watch the blue sunset and think, this is my day ending. This is my night beginning. Just 37 minutes slower than the world I left behind. Mars is small, not tiny, but noticeably smaller than Earth, about half our diameter, to be more precise. In the family portrait of our solar system, Mars is the runt. Only Mercury is smaller among the planets. If Earth were a basketball, Mars would be a softball. You could hold it in 2 hands, if such a thing were possible. And yet, despite its modest size, it occupies an enormous place in our imagination. More missions have been sent to Mars than to any other planet. More rovers have trundled across its surface. More orbiters have mapped its terrain. Size isn't everything, it turns out. What Mars lacks in volume, it makes up for in potential. Its smaller size means lower gravity, easier to land on, easier to launch from. Its reduced mass means it cooled faster than Earth, shutting down its magnetic field earlier, yes, but also preserving ancient geology that might have been recycled away on a larger, more geologically active world. And there's something about its size that makes it feel achievable. Venus is closer, but it's a hellscape of sulfuric acid clouds and crushing atmospheric pressure. Jupiter and Saturn are magnificent, but they're gas giants. There's no surface to land on, no soil to plant a flag in. Mars is manageable. Challenging, certainly. Deadly, absolutely. But within the realm of human ambition, a small world with big possibilities. The second smallest planet, carrying the weight of humanity's off-world dreams. Mars is tilted at about 25 degrees on its axis. Earth is tilted at 23.5 degrees. This is another one of those cosmic coincidences that makes Mars feel like a distant cousin, different enough to be interesting, similar enough to be familiar. And that tilt means Mars has seasons, just like Earth does. Spring, summer, fall, winter, the same 4-part rhythm that governs harvest cycles and migration patterns and the falling of leaves. But here's where it diverges. Because Mars takes 687 Earth days to orbit the Sun, each Martian season lasts nearly twice as long as ours. Spring on Mars stretches for 7 months. Winter settles in and stays. Imagine that. Imagine summer starting in January and not ending until August. Imagine autumn leaves, if there were trees, if there were leaves, holding their colors from September until April. The polar ice caps grow and shrink with these long seasons. In the Martian winter, carbon dioxide from the atmosphere freezes directly onto the ice caps as dry ice, solid CO2 accumulating in layers. Then when spring arrives, that dry ice sublimates, evaporating directly from solid to gas, releasing the carbon dioxide back into the air. The planet breathes, slowly, patiently, inhaling for months, exhaling for months. If you lived on Mars, you'd need a different kind of patience. Seasons wouldn't mark months. They'd mark half a year or more. You'd plant in the spring and wait twice as long for harvest. You'd endure winters that seemed endless and summers that felt like they might never fade. But the rhythm would be there, the familiarity, the sense that time moves in circles, that the cold always gives way to warmth, that nothing lasts forever, not even a Martian winter. Stand on the surface of Mars and you'd be breathing. Well, no, you wouldn't be breathing at all, not without a pressure suit, because the atmosphere on Mars is about 100 times thinner than Earth's, 100 times. It's hard to grasp what that means without comparison. The air pressure on Mars is roughly equivalent to the pressure at 100,000 feet altitude on Earth, 3 times higher than commercial jets fly, well into the realm of space by most definitions. It's composed mostly of carbon dioxide, around 95%, with tiny amounts of nitrogen, argon, and trace gases. There's almost no oxygen, no nitrogen in the concentrations needed for biology, no ozone layer to filter ultraviolet radiation. And yet, technically, it's still an atmosphere. There's weather, dust devils spin, dust storms grow, clouds form, but you could stand in the middle of a Martian dust storm, one of those planet-spanning tempests that block out the sun for months, and barely feel a breeze. The wind might be blowing at 60 miles per hour, but with so little air, it would feel gentle. Insistent, maybe, but gentle. This thinness is both a curse and a blessing. A curse because it means Mars can't hold heat, can't shield against radiation, can't support liquid water on its surface. But a blessing because it means spacecraft can land more easily. There's atmosphere enough to use parachutes, but not so much that heat shields burn away. It's an atmosphere that exists in a strange liminal space, enough to matter, not enough to protect, enough to create weather, not enough to sustain life. A whisper of an atmosphere, really, the ghost of what Mars once had, back when it was warmer, wetter, and perhaps alive. Mars has 2 moons, and their names are perfect, Phobos and Deimos, fear and panic. They're named after the sons of Ares, the Greek god of war, who accompanied their father into battle. Where Ares went, fear and panic followed, and now they orbit Mars, forever circling their namesake planet, bound by gravity to stay close. But these aren't moons like our moon. They're not spherical, they're not large. Phobos is only about 14 miles across at its widest. You could drive around it in an afternoon, if there were roads, and you could somehow keep your car on the surface. Deimos is even smaller, just 7.5 miles wide. They're lumpy, potato-shaped rocks, covered in craters and dust. Most scientists think they're captured asteroids. wayward rocks that wandered too close to Mars billions of years ago and got trapped in its gravitational embrace. They're not children of Mars, they're adopted, strangers who became permanent residents. And there's something melancholic about them, especially Phobos, because Phobos orbits so close to Mars that tidal forces are slowly pulling it inward. Every century, it drops about 6 feet closer. In 50 million years, maybe sooner, Phobos will either crash into Mars or be torn apart by tidal stress, creating a temporary ring system around the planet. Fear is falling, slowly, inevitably, but for now, they remain. Two small, dark shapes crossing the Martian sky, rising and setting at odd times, casting shadows that move faster than Earth's moon ever could. Companions to a lonely planet, reminders that even Mars, distant and cold, doesn't orbit entirely alone. Olympus Mons is the largest volcano in the solar system, and it's difficult to convey just how enormous it is without using comparisons that themselves feel impossible. It stands about 13.6 miles high, nearly 3 times the height of Mount Everest. If you could somehow place it on Earth, its base would cover an area roughly the size of Arizona. 300,000 square miles of shield volcano, built up over millions of years by lava flows piling on top of lava flows, with no plate tectonics to move it away from its hot spot. But here's what makes it truly strange. If you were standing on Olympus Mons, you might not even realize you were on a mountain. The slopes are so gentle, averaging just about 5 degrees, that if you were walking up them, it would feel like a mild hill. You could hike for days and barely notice the incline. And because the mountain is so vast, the base would curve away beyond your horizon in every direction. You wouldn't see the peak, you wouldn't see the edges. You'd just be walking uphill on what felt like endless, gently sloping terrain. And if you somehow made it to the summit, 13.6 miles up, standing on the edge of the caldera, you'd look down, and the base of the mountain would still be beyond the horizon. The curvature of Mars itself would hide it from view. It's a mountain so large it transcends what we think of as mountain. It's a geological feature on a scale that doesn't exist on Earth, a monument to Mars' volcanic past, when lava flowed freely and the planet's interior was hot enough to push molten rock to the surface for millions of years. Now, Olympus Mons is quiet, dormant most likely, perhaps extinct. The lava has cooled, the eruptions have ceased, but the mountain remains, a frozen giant, slowly eroding under wind and dust, but still towering, still the tallest peak in the solar system. If Olympus Mons is Mars's crown, then Valles Marineris is its scar. This canyon system stretches over 2,500 miles across the Martian surface, long enough to span the entire continental United States, from New York to Los Angeles. It's about 125 miles wide at its broadest points, and in places it plunges nearly 4 miles deep. The Grand Canyon, by comparison, is a scratch. Valles Marineris is 4 times deeper, 20 times wider, and 10 times longer. If you stood on one rim, the other side would be invisible, lost beyond the curve of the planet. We're not entirely sure how it formed. It might be a tectonic crack, a rift where the Martian crust started to pull apart billions of years ago and then froze in place, preserved because Mars lacks the active geology to heal or recycle such features. Or it might have been carved, at least in part, by water. Catastrophic floods that scoured the landscape when Mars was younger and wetter. Probably it's both. a crack that was then widened by erosion, by water, by landslides that collapsed entire cliff faces into the depths below. There are places within Valle Marineris where layered rock formations are exposed, strata that represent millions of years of Martian history, laid bare like pages in a book. Each layer tells a story: volcanic ash, wind-blown dust, ancient lake beds. Geologists dream of exploring those walls, reading the biography of Mars written in stone. But for now, Valles Marineris remains empty. No rivers run through it anymore. No wind strong enough to carry sound echoes through its chambers. It's a silent canyon, vast and patient, waiting for the day when human eyes might finally see it up close, when explorers might stand on its rim and feel what it's like to look into a chasm that dwarfs anything Earth has to offer. A scar on the face of Mars, a reminder of violence or water or both. A canyon so large it changes the planet's shape. Gravity on Mars is about 38% of Earth's. That means if you weigh 100 pounds on Earth, you'd weigh just 38 pounds on Mars. Imagine that for a moment. Imagine feeling lighter, not just emotionally, but physically. Your legs, used to carrying your full Earth weight, would suddenly be supporting less than half. You'd feel buoyant almost, springy. You could jump nearly 3 times higher than you can on Earth. A simple hop would carry you several feet into the air, and when you fell, you'd fall slowly, drifting back down in what would feel like slow motion, giving you plenty of time to adjust your landing. But this isn't entirely a gift. Your muscles, evolved and strengthened under Earth's gravity, would begin to atrophy. Bones would lose density. Astronauts on the International Space Station lose about 1 to 2% of their bone mass per month in microgravity, even with rigorous exercise. On Mars, the gravity is low enough that similar effects would occur, though slower. You'd need to exercise constantly. Resistance training, weight-bearing activities, anything to convince your body that it still needs strong bones and muscles, even though the planet is no longer demanding them. And there's something strange about living in reduced gravity that's hard to articulate until you experience it. Your proprioception, your body's sense of where it is in space, is calibrated for Earth. On Mars, you'd move differently, pour water differently, drop things and watch them fall at an unfamiliar speed. It would take time to adjust, time to rewire your instincts. But imagine the children born there, the first generation of Martians. They'd grow up light. They'd never know what it's like to feel Earth's pull. And if they ever visited Earth, our gravity would feel crushing, oppressive. They might not even be able to walk here without assistance. Mars would feel like freedom to them. Earth would feel like a prison. Gravity shapes us more than we realize, and on Mars, it would shape us differently. The first successful Mars landing happened on July 20th, 1976. Viking 1 touched down in a region called Krysplanchia, the Plains of Gold, and sent back the first clear images from the surface of another planet. Those photographs were grainy, black and white at first, then color. They showed rocks, dust, a salmon-colored sky. The horizon curved gently in the distance. It looked like a desert, not the romantic canals and cities that early astronomers had imagined, but a real physical place. Desolate, yes. Empty, certainly, but real. People gathered around televisions to see these images. Scientists stared at them for hours, analyzing every pixel. This was Mars. Not as a point of light in the sky, not as a fuzzy disk through a telescope, but as ground you could theoretically walk on, rocks you could pick up, dust that would stick to your boots. Viking 1 carried instruments to search for life. It scooped up Martian soil and ran experiments designed to detect biological activity. The results were ambiguous. One experiment showed a reaction that could have been biological, or could have been chemical. Scientists argued then, and still argue now, about what Viking 1 actually detected. But regardless of whether it found life, Viking 1 proved something crucial. We could land on Mars. We could send machines to its surface, and they could survive, at least for a while. Viking 1 operated for over 6 years before its batteries finally failed, and somewhere in Chryse Planitia it still sits, silent now, covered in dust, a monument to human curiosity, the first artificial object to successfully touch Mars and tell us what it found. A year on Mars lasts 687 Earth days, nearly twice as long as our year. Time moves differently there, in ways that would fundamentally reshape how you think about age, seasons, and the passage of time itself. If you were born on Mars, your first birthday wouldn't arrive until you were almost 2 Earth years old. By the time you turned 10 on Mars, you'd be nearly 20 by Earth's calendar. Age would become ambiguous. Are you counting Martian years or Earth years? Which one matters more? For colonists, this would create a strange duality. They might celebrate holidays on an Earth calendar to maintain connection with home, but live their agricultural and work cycles according to Mars' natural rhythms. New Year's would come twice, once for Earth, once for Mars. You'd exist in 2 timelines simultaneously. And think about what this means for memory and perception. A year feels like a long time to us because it contains all 4 seasons, all the holidays, the cycle from winter back to winter again. On Mars, that same psychological cycle would take twice as long to complete. Would time feel slower? Would patience become a cultural virtue, a necessity bred into Martian society? Or maybe the opposite would happen. Maybe living on a world where years stretch longer would make people more focused on the present moment, less concerned with annual milestones, and more attuned to daily rhythms. Either way, a Martian year is a reminder that time isn't universal. It's planetary, local. A year is just one trip around the sun, and depending on where you're orbiting from, that trip takes a very different amount of time. 687 days to complete one circuit. Almost 2 Earth years to watch Mars return to the same point in its orbit. A longer dance around the same star. The average temperature on Mars is about 80 degrees, which is colder than Antarctica in the depths of winter. But average is misleading because Mars experienced temperature swings that would be unthinkable on Earth. Near the equator on a summer afternoon, temperatures can climb above freezing, maybe even reaching a pleasant 70 degrees at ground level. But that same night, in that same spot, temperatures can plummet to 100 degrees or lower. A 100-degree temperature swing between noon and midnight, every single day. This happens because Mars has such a thin atmosphere. On Earth, our thick blanket of air holds heat, moderating temperature changes. The greenhouse effect keeps nights from getting too cold, keeps days from getting too hot. But Mars has no such buffer. When the sun is up, its warmth hits the ground directly, heating the surface. But the moment the sun sets, that heat radiates back into space. There's nothing to hold it in. Imagine what it would be like to live there. You'd need habitats with incredible insulation, heating systems that could compensate for the cold, spacesuits designed to handle both the warmth of day and the brutal cold of night. And yet, there's something poetic about it. Mars doesn't hold on to anything, not heat, not water, not atmosphere. It lets everything go. The sun's warmth arrives and departs. The seasons come and pass. Ice forms and sublimates. Mars exists in a state of constant letting go, unable or unwilling to hold on to the things that make Earth so habitable. It's a cold world, not just in temperature but in spirit. A world that has released its warmth and now waits, frozen, patient, under a thin sky that can't protect it from the void. Mars has ice caps at both poles, white crowns that grow and shrink with the seasons, visible even through amateur telescopes from Earth. These aren't just frozen water, though water ice is certainly there. They're layered structures, water ice mixed with frozen carbon dioxide, dust, and sediment. In winter, the carbon dioxide in the atmosphere freezes directly onto the poles as dry ice, sometimes several feet thick. Then in spring, that dry ice sublimates away, evaporating back into the atmosphere without ever becoming liquid. This seasonal freezing and thawing is dramatic. In winter, up to 25% of Mars's atmosphere freezes out of the air and deposits at the poles. The atmospheric pressure across the entire planet drops measurably. Then in spring, that CO2 returns to the atmosphere, and the pressure rises again. The planet breathes, literally. Inhaling carbon dioxide in winter, exhaling it in summer. Beneath the seasonal caps of dry ice lie permanent caps of water ice, especially at the North Pole. These permanent ice deposits are miles thick in places, containing more water than Lake Superior. It's frozen, of course, locked away at temperatures far below zero, but it's there. Scientists have even detected what might be liquid water beneath the southern ice cap. Subglacial lakes kept liquid by pressure and salts, similar to the lakes beneath Antarctica's ice sheets. If confirmed, these would be some of the only places on modern Mars where liquid water exists. The poles are archives too. The ice contains layers like tree rings, each layer representing a different climate era. Dust storms that raged thousands of years ago left their mark in dark layers. Clearer ice represents calmer times. Scientists dream of drilling into these caps, extracting ice cores that would tell the story of Martian climate going back millions of years. But for now, the poles remain pristine, frozen libraries waiting to be read. The last repositories of Mars' lost water, waiting in cold storage for a warmer age that may never come. From Mars, Earth would appear as a bright blue star, not a disk, not a crescent, just a point of light, brighter than most stars, with a slight blue tint if your eyes were sharp enough to detect it. And next to it, barely separated, would be another dimmer point, our moon, visible as a companion to Earth's light. Imagine standing on Mars at sunset, watching the blue sun dip below the horizon, and then looking up as true darkness falls. There, among the constellations, the same constellations visible from Earth, barely changed by perspective, would be your home. A blue dot, pale, small, 35 million miles away at its closest, 250 million miles away at its farthest. You could see it with your naked eye, even through the dusty Martian atmosphere. But you couldn't see continents, couldn't see oceans, couldn't see the lights of cities or the movement of clouds. Just a steady blue point, rising and setting with the stars, reminding you that somewhere on that distant speck, Everyone you'd ever known was living their lives. There's something profoundly lonely about that image, but also something comforting. You're not truly alone if you can still see home. Distance becomes relative. Yes, you're millions of miles away. Yes, radio signals take between 4 and 24 minutes to travel between Earth and Mars, depending on where the planets are in their orbits. But you can still see it, still point to it and say, there. Astronauts on the moon could look up and see Earth as a large, blue marble, close enough to show clouds and continents. But Martian colonists would have no such comfort, just a blue star, a reminder of how far they've come and how small Earth really is when seen from the perspective of another world. A pale blue dot, just like Carl Sagan described, but this time you'd be the one looking back at it across the dark. Mars once had rivers, real rivers, with flowing water, carving valleys, and depositing sediment meandering across a younger, warmer planet. We know this because the evidence is still there, written in the landscape. Orbital images show dried river valleys, some of them thousands of miles long, branching like the veins in a leaf. They have the same dendritic patterns that rivers on Earth create, tributaries flowing into larger channels, carrying water from highlands down to lowlands. Some of these valleys are deep, wide, the kind of channels that couldn't have been carved by wind or lava. They required water, lots of it, flowing steadily over long periods of time, not just flash floods, but sustained rivers that persisted for years, centuries, maybe millennia. There are even deltas, fan-shaped deposits where rivers once emptied into lakes or seas, dropping their sediment load as the water slowed. Jezero Crater, where the Perseverance rover currently explores, contains one of the best preserved deltas on Mars. The layers are still visible, still showing the exact pattern that rivers create when they meet standing water. But here's what's haunting. Those rivers are gone, completely dry, not frozen, dry. The water that carved them vanished billions of years ago, either lost to space when Mars's atmosphere thinned, or locked underground as ice, or chemically bound into minerals. What must it have been like when those rivers flowed? Rain falling, water rushing over rocks, the sound of flowing water echoing through canyons, maybe mist rising from waterfalls, maybe ice forming at night and melting by day. An entire hydrological cycle, evaporation, precipitation, runoff, all happening on a planet that is now a frozen desert. The riverbeds remain as ghosts, dry channels cutting through ancient rock, leading nowhere now, carrying nothing but wind and dust. Reminders of a Mars that was, in some ways, more like Earth than the Mars we see today. Mars used to have a much thicker atmosphere, perhaps dense enough to support liquid water, to trap heat, to create weather systems complex enough to generate rain. We know this from multiple lines of evidence. The erosion patterns require an atmosphere thick enough to support sustained weather. The isotope ratios in Martian rocks suggest significant atmospheric loss. The very fact that water once flowed on the surface means the atmosphere must have been denser, because at current pressures, liquid water can't exist. But around 4 billion years ago, Mars lost its magnetic field. We're not entirely sure why. Possibly a massive asteroid impact, possibly the natural cooling of its core. But once the magnetic field vanished, Mars lost its shield against the solar wind. The solar wind is a stream of charged particles constantly flowing out from the sun. Earth's magnetic field deflects these particles, protecting our atmosphere. But Mars, without its magnetic shield, stood naked before this cosmic breeze. And slowly, over hundreds of millions of years, the solar wind stripped away Mars' atmosphere, particle by particle, molecule by molecule. The lighter isotopes escaped first, leaving behind a residue enriched in heavier isotopes, a fingerprint of loss that we can still detect today. The process continues even now. NASA's MAVEN spacecraft has observed Mars losing about 100 grams of atmosphere to space every second. That doesn't sound like much, and it isn't on human timescales. But over geological time, it adds up. Mars is still bleeding air into space, still losing the remnants of an atmosphere that was once thick enough to blanket a living world. It's a slow death, not dramatic, not sudden, just a gradual thinning, a fading, a letting go that has been happening for billions of years and will continue for billions more. Mars once had an atmosphere. Now it has the ghost of one. And someday, even that ghost might vanish entirely. Scientists estimate that ancient Mars held enough water to cover its entire surface in an ocean about 450 feet deep. If concentrated in the northern lowlands, where evidence suggests it actually was, that ocean might have been nearly a mile deep in places. An ocean on Mars. Not a metaphor, not a poetic exaggeration, but an actual body of liquid water, with waves and currents and a shoreline where water met land. Imagine standing on that shoreline billions of years ago. The water would be cold, probably. The sun would appear smaller, dimmer, because Mars is farther out. But there would be sound, waves lapping, wind blowing across the water's surface, maybe ice forming at night and cracking as temperatures rose during the day. Some of that water evaporated and was lost to space. Some seeped into the ground and froze, becoming part of the permafrost that still exists beneath much of the Martian surface. Some was chemically incorporated into rocks, locked into the crystal structure of minerals. But it didn't truly vanish. It transformed, spread out, hid. Orbital radar has detected vast quantities of subsurface ice, especially at mid-latitudes. In some places, this ice is just a few feet beneath the surface, buried under dust and regolith. In other places, it's miles deep, ancient glaciers that flowed when Mars was younger. There's more water on Mars than most people realize. It's just not liquid, not accessible, not flowing in rivers or filling oceans. It's frozen, waiting, a planet's worth of water, still present but locked away, like a fortune buried and forgotten. If humans ever establish a permanent presence on Mars, they won't need to bring water from Earth. They'll mine it, drill down, melt ice, purify it. The ocean that once covered Mars will, in a sense, return, not to the surface, but to greenhouses and habitats, to drinking bottles and irrigation systems. The water never left. It's still there, just sleeping. About 4 billion years ago, Mars had a global magnetic field, much like Earth does today. We know this because patches of Mars crust still retain magnetization. Fossil magnetic fields, frozen into ancient rocks. These magnetized regions are scattered across the surface, especially in the southern highlands. They're like memories, preserved in stone. Each one represents a time when Mars had an active magnetic field, when its core was hot and churning, generating the electromagnetic forces that protected the planet. Then something happened. Maybe a massive asteroid impact disrupted the core's convection. Maybe the core simply cooled to the point where it could no longer sustain the dynamo effect needed to generate a magnetic field. We don't know for certain, but the magnetic field died. And with it, Mars lost its primary defense against the solar wind. Earth's magnetic field does more than make compasses work. It creates a protective bubble, the magnetosphere, that deflects charged particles from the sun. Without it, those particles strike the atmosphere directly, slowly stripping it away. Mars still has localized magnetic fields in those ancient crustal rocks, but they're weak, patchy, insufficient to protect the planet. It's like wearing armor that's rusted through, better than nothing, but not by much. Some scientists have proposed that we could, theoretically, give Mars an artificial magnetic field. Place a powerful electromagnet at the L1 Lagrange point between Mars and the Sun, creating a shield that would deflect the solar wind. It sounds like science fiction, and with current technology it is. But it's not physically impossible. If we could restore Mars's magnetic field, the planet might slowly begin to thaw. Atmosphere would stop escaping. Gases trapped in the ice and soil might sublimate into the air. Over thousands or millions of years, Mars could become warmer, thicker aired, more hospitable. But for now, Mars remains unshielded, exposed, vulnerable to the same solar wind that has been eroding it for billions of years. The northern hemisphere of Mars is strangely smooth and low-lying compared to the cratered southern highlands. This dramatic difference, called the Martian dichotomy, is one of the planet's most puzzling features. The northern lowlands sit about 3 miles lower in elevation than the southern highlands, and they're remarkably flat, with far fewer impact craters. This suggests the northern surface is younger, resurfaced by some process that erased ancient craters. One hypothesis: the northern lowlands are the floor of an ancient ocean. If true, this would have been a massive body of water, covering roughly a third of the planet's surface, larger than Earth's Atlantic Ocean, deep enough in places to drown mountains. Scientists have found what might be ancient shorelines, bands of similar elevation that circle the northern lowlands, exactly where you'd expect to find a coastline. But these features are subtle, eroded by billions of years of wind and dust, and not everyone agrees they're truly shorelines. Still, the evidence accumulates. Minerals that form in water, sedimentary rocks that look like they were deposited in standing water, smooth plains that resemble ocean basins. If the northern ocean existed, it would have been cold, ice-covered, probably, for much of the Martian year. But beneath that ice, there could have been liquid water. And where there's liquid water, there's potential for life. This is where the stakes get higher. Because if Mars had an ocean that persisted for millions of years, that changes everything. Life on Earth emerged in the ocean. If Mars had oceans, and if chemistry is chemistry regardless of planet, then those oceans might have hosted life too. We haven't proven the ocean existed, but the northern lowlands are there, smooth and low and suggestive. A dried seabed, perhaps. Or perhaps just a lowland plain created by some other geological process we don't fully understand yet. Either way, it's a feature large enough to reshape a planet's hemispheres, and empty enough to make you wonder what once filled it. There are these strange dark streaks on Mars called recurring slope lineae, RSL for short, that appear on steep slopes during warm seasons and then fade during cold seasons. They were first noticed in high-resolution orbital images around 2011. Dark lines, almost like wet stains, flowing down crater walls and canyon sides. They appear in late spring, grow darker and longer through summer, then fade and disappear by winter. And the next year they come back. Same slopes, same patterns. The obvious question, is this water? It would make sense. On Earth, when water seeps through soil, it darkens the surface, and the seasonal timing fits perfectly, appearing when temperatures rise above the point where briny water could exist, disappearing when it gets too cold. But here's the problem. Liquid water shouldn't be stable on Mars's surface. The atmospheric pressure is too low. Pure water would either freeze or boil away almost immediately, unless it's not pure water. Salt water, brine, can remain liquid at much lower temperatures and pressures than pure water. If the Martian soil contains perchlorates, which it does, and if that soil gets damp, you could have temporary flows of extremely salty water, cold enough to freeze your hand instantly, but liquid enough to flow downhill. Or maybe it's not water at all. Maybe it's dry granular flow, sand and dust sliding down slopes in a way that darkens the surface without any liquid involved. Some scientists lean toward this explanation now, especially since spectroscopic analysis hasn't definitively detected water in these features. The truth is, we don't know for certain, and that uncertainty is part of what makes Mars so compelling. We have incredible cameras in orbit. We have rovers on the surface. We have decades of data. And still, we can't agree on whether these dark streaks are water flowing on Mars today, or just dust falling in patterns that happen to look like water flows. Maybe it's both, in different locations. Maybe some RSL are briny seeps, and others are dry flows. Or maybe we're missing something entirely, some process unique to Mars that we haven't thought of yet. But every spring, as Mars warms, those dark streaks appear, growing, flowing, fading, and we watch and wonder and argue about what they mean. Mars is covered in minerals that only form in the presence of liquid water. Not ice, liquid water specifically. Hematite, for instance. Iron oxide that forms when iron is exposed to water and oxygen. It's been found in vast deposits, especially in a region called Meridiani Planum, where the Opportunity rover spent years exploring. Clays, phyllosilicates, to be precise. These form when volcanic rock interacts with water over long periods. The water chemically alters the minerals, creating clays that are stable, layered, and unmistakably the product of aqueous processes. Orbital spectrometers have detected clay deposits across Mars, particularly in ancient terrain. Sulfates, carbonates, silica deposits. Each one tells a story about water, where it pooled, how long it persisted, whether it was acidic or neutral, salty or fresh. The rocks themselves are witnesses. They can't speak, but they remember. Every atom in their crystal structure is a record of the conditions under which they formed, and what they remember is water. Not just brief surface moisture, not just frost condensing and sublimating. Long-term liquid water, standing water, water that soaked into rock and reacted with minerals over thousands or millions of years. This is what makes the search for past life on Mars so tantalizing, because everywhere we find these minerals, we find evidence of a habitable environment. Not necessarily inhabited, but habitable. The chemistry was right. The temperature was right, at least periodically. The water was there. If life is just chemistry that got complicated enough to reproduce, then Mars had all the ingredients: water, minerals, energy from sunlight or chemical reactions, time, millions upon millions of years of time for chemistry to experiment, to find stable configurations, to stumble upon self-replication. We don't know if it happened, but the minerals prove it could have. The recipe was there. Whether anything ever cooked from it remains one of the deepest mysteries we're trying to solve. Gale Crater is where the Curiosity rover has been exploring since 2012, and what it's found there is remarkable. Evidence that the crater once contained a lake that persisted for potentially millions of years. Not a puddle, not a temporary flood deposit, a lake. Deep enough to have layers, oxygenated water near the surface, different chemistry at depth. Stable enough to deposit sediments in distinct layers, like the pages of a book recording different chapters of environmental conditions. Curiosity has drilled into these ancient lakebed deposits and analyzed their chemistry. The results paint a picture of a lake that would have been, by Earth standards, habitable. Neutral pH, not too salty, not too acidic. Minerals dissolved in the water that microbes could have used for metabolism. And the lake wasn't just sitting there stagnant. Streams fed into it, carrying fresh water and nutrients down from the crater rim. The lake level rose and fell with climate variations. Sometimes it might have frozen over. Other times it might have been liquid, reflecting a younger, warmer sky. How long did it last? That's harder to determine precisely. But the thickness of the lakebed sediments suggests at least tens of thousands of years, possibly much longer. Long enough for life to emerge. If life is something that emerges given the right conditions and enough time. Curiosity hasn't found fossils, hasn't found DNA or cell walls or any unambiguous signs of biology. But it has found organic molecules, carbon-based compounds that could be biological in origin, or could be from meteorites, or could be from non-biological chemical processes. The ambiguity remains, but here's what we know for certain. Gale Crater held a lake, and that lake was a place where life, if it existed anywhere on Mars, could have thrived. Imagine standing at the shore of that ancient lake on a cold Martian morning. Water lapping at your feet, mountains rising in the distance, their slopes carved by erosion, clouds moving overhead, and beneath the surface, in the mud and minerals, maybe, just maybe, something alive. Something small and simple, but alive nonetheless. The lake is gone now, dried up billions of years ago, but its memory remains, written in the rocks that Curiosity slowly, methodically reads. Mars's axial tilt isn't stable like Earth's. While Earth wobbles only a degree or two over thousands of years, thanks to the stabilizing influence of our large moon, Mars wobbles wildly. Over cycles of about 50,000 to 2 million years, Mars's tilt varies between 15 and 35 degrees. Right now it's at 25 degrees, comfortably in the middle. But it's been as low as 15 degrees and as high as 35 degrees in the geologically recent past. Why does this matter? Because axial tilt determines seasons, and seasons determine climate, and climate determines where ice accumulates and where it melts. At low tilt, Mars is more upright. The poles receive less extreme seasonal variation, and ice tends to accumulate there, building up thick polar caps. The equator becomes drier, colder. At high tilt, the poles point more directly toward or away from the sun during their respective summers. The polar ice caps can partially sublimate, releasing water vapor and CO2 into the atmosphere. Some of that ice then migrates toward mid-latitudes, or even the equator, where it can fall as snow or frost. Mars essentially experiences catastrophic climate shifts every 50,000 years or so. Ice ages and thaw periods, but driven by changes in axial tilt rather than changes in orbit. This wobbling is part of why Mars is so challenging to understand. The planet we see today, with ice concentrated at the poles and a dry equator, is just one snapshot in a constantly shifting climate system. 10,000 years ago, Mars might have had snow at mid-latitudes. 10,000 years from now, it might have ice sublimating from the poles and thickening the atmosphere slightly. It's a planet that can't settle down, that cycles through climate states on timescales short enough that we might actually observe changes if we watched long enough. A world in constant flux, wobbling through its ages, never quite finding equilibrium. Some of the ancient riverbeds on Mars show evidence of water flows that carved channels deeper than the Mississippi River. These aren't gentle streams. These are massive channels, sometimes miles wide, with features that suggest violent, sustained flow. Streamlined islands, scoured bedrock, cataracts where water plunged over cliffs, cutting deep plunge pools into the rock below. The scale is staggering. Some outflow channels appear to have been carved by floods that dwarfed anything in Earth's history. Catastrophic releases of water, perhaps from underground aquifers that suddenly breached the surface, or from ice-dammed lakes that failed and released their contents all at once. Imagine the sound, not the gentle babbling of a creek, but a roar, billions of gallons of water rushing through canyons, carrying boulders, carving rock, reshaping landscapes in days or weeks. And then, silence. The water flowed, carved its mark, and vanished. Either it froze or soaked into the ground, or evaporated into the thin air. The channels remain empty now, wind-blown and dust-covered, but still showing the unmistakable signature of flowing water. These channels are proof that water on ancient Mars wasn't just present, it was dynamic, powerful, capable of reshaping the landscape in dramatic ways. Where did all that water come from? And where did it go? The most likely answer is that Mars had vast amounts of subsurface ice and groundwater trapped beneath frozen layers. When volcanic activity or impacts provided heat, that ice melted catastrophically, bursting out onto the surface in floods that carved these massive channels before the water froze or evaporated. It's a vision of Mars that's simultaneously more alive and more violent than the quiet desert we see today. A world where ice and water battled for dominance, where catastrophic floods periodically resurfaced the landscape, where the ground itself could split open and release torrents. Now those channels lie quiet, preserved in the dry Martian air, waiting for someone to trace their lengths and wonder what it sounded like when water last flowed through them. Over 350 meteorites found on Earth originated from Mars. Pieces of Mars, blasted off the planet's surface by asteroid impacts, wandering through space for millions of years before falling to Earth. Think about the violence required to make this happen. An asteroid strikes Mars with enough force to excavate rock and launch it into space at escape. Velocity over 3 miles per second. The impact creates a crater, vaporizes some of the target rock, melts more, and flings fragments on trajectories that carry them away from Mars entirely. Those fragments orbit the Sun, some for just a few years, others for millions of years. Eventually, some of them intersect Earth's orbit. They enter our atmosphere, burning brightly as meteors, and land as meteorites. Pieces of Mars still bearing the chemical and mineralogical fingerprints of their origin. How do we know they're from Mars? Several ways. The gases trapped in tiny pockets within the rock match the composition of Mars' atmosphere as measured by Viking landers. The minerals match what we see in Martian rocks. The formation ages correspond to Martian volcanic activity. These meteorites are extraordinary resources. They're free sample return missions. We didn't have to launch a rocket to Mars, scoop up rocks, and bring them back. Mars sent them to us, courtesy of cosmic collisions. And some of these meteorites contain fascinating features. One of them, designated ALH 84001, contains tiny structures that some scientists argued might be fossilized bacteria. Most scientists now think these structures are non-biological, formed by chemical processes rather than life. But the debate shows how tantalizing these rocks are, how every mineral grain, every microscopic feature is scrutinized for signs of past life. Somewhere on Mars, there are craters where these rocks came from, impact sites where debris was ejected into space. We'll probably never find the exact craters. They could be anywhere, and millions of years of weathering have obscured their features. But they're there, connection points between Earth and Mars, written in stone. You can hold a piece of Mars in your hand if you visit the right museum. A rock that fell from the sky, carrying stories encoded in its crystal structure. A messenger from another world. Jezero Crater is where NASA's Perseverance rover landed in February 2021, and it's one of the most geologically rich sites ever chosen for Mars exploration. Jezero is an ancient impact crater, about 28 miles wide, with high walls and a relatively flat floor. But what makes it special is the delta, a fan-shaped deposit on the western side of the crater, where a river once flowed in from the surrounding highlands. On Earth, deltas form when rivers carrying sediment slow down as they enter a standing body of water, a lake or sea. The water velocity drops, and the sediment falls out, building up layer by layer. Over time, these layers create distinctive fan shapes, with branching channels where the river distributaries spread out. Jezero's delta is textbook. You can see the layers from orbit, stacked like pages. You can trace the ancient river channel leading into the crater. You can identify where water once pooled behind the crater rim before breaching through and filling Jezero with a lake. This delta existed around 3 to 5 billion years ago, during a time when Mars was transitioning from its wet period to its current dry state. The lake might have lasted for millions of years, fed by rivers, slowly depositing sediments that preserved whatever organic or inorganic chemistry was happening at the time. Deltas on Earth are often rich in organic material. Rivers carry nutrients from the surrounding landscape, concentrating them in delta sediments. If life existed in Jezero's lake, the delta would be the most likely place to find evidence of it. That's why Perseverance is there. It's drilling into delta rocks, collecting samples, sealing them in tubes that a future mission will retrieve and bring back to Earth. Those samples might contain biosignatures, chemical or physical evidence of ancient life. Or they might contain complex organic chemistry that stopped just short of becoming life. Or they might reveal nothing biological at all, just minerals and chemistry that tell us about ancient Martian environments. But the delta is there, preserved for billions of years, a snapshot of a time when water flowed into Jezero, when a lake reflected the sky, when rivers carried stories written in sediment. And we're reading those stories now, grain by grain, slowly piecing together what happened in this ancient crater lake so long ago. Mars has massive deposits of underground ice, especially near the poles, containing more water than Lake Superior. This isn't a guess. We've detected it with ground-penetrating radar, with spectroscopy, with direct observation where erosion has exposed ice at the surface. In some regions, you could dig down just a few feet and hit solid water ice. The ice is mixed with soil, a frozen mixture called permafrost, similar to what exists in Earth's Arctic regions. But unlike Earth's permafrost, which is confined to polar and high-latitude regions, Martian permafrost extends much farther toward the equator, preserved by the planet's consistently cold temperatures. This ice represents a resource almost beyond calculation for future Mars missions. Water is heavy. Carrying enough water from Earth to support even a small crew would require massive amounts of rocket fuel. But if you can mine water on Mars, everything changes. You can drink it, obviously. You can use it for growing food in hydroponic systems. You can split it into hydrogen and oxygen. Oxygen for breathing, hydrogen and oxygen together as rocket fuel. A single ice deposit could support a Mars base indefinitely. But more than that, this ice is a relic. It's ancient water, frozen for potentially billions of years. Drilling into it would be like drilling into an archive. Each layer represents a different climate era, a different atmospheric composition. The ice might contain trapped bubbles of ancient Martian air, preserved like insects in amber. And if there's life on Mars today, microbial life, clinging to existence in hidden refuges, the subsurface ice is where we might find it, deep enough to be protected from radiation, cold enough to preserve organic molecules, possibly containing liquid water at depth where pressure and salts could keep it from freezing. The ice is there, waiting, a frozen ocean distributed across the planet's subsurface, not flowing, not accessible without effort, but present, patient, holding more water than the largest of Earth's Great Lakes, locked in cold storage beneath rust-colored dust. Around 3.5 billion years ago, Mars underwent a fundamental transformation. It changed from a warm, wet world, with rivers and lakes and possibly an ocean, to the cold, dry desert we see today. This didn't happen overnight. It took hundreds of millions of years, but compared to geological timescales, it was relatively rapid. Rapid enough that we can see a clear before and after in the rock record. Before, clay minerals that form in neutral pH water, riverbeds with braided channels suggesting persistent flow, lakebed deposits with seasonal layers, chemical signatures of a thicker atmosphere, after sulfates that form in acidic, evaporating water, dry channels, minerals that suggest arid, oxidizing conditions, an atmosphere too thin to support liquid water. What caused this transition? Probably multiple factors acting together. The loss of the magnetic field meant the solar wind could strip away atmosphere more efficiently. Volcanic activity declined as the planet cooled, meaning less gas was being replenished from the interior. Water soaked into the ground and froze, creating permafrost that locked it away. Surface water evaporated, and without a thick atmosphere to hold it in, much of it was lost to space. It's possible there were intermediate periods, epochs where the climate briefly warmed again, when orbital variations temporarily created more favorable conditions. The transition might not have been smooth, but rather a series of wet periods and dry periods, with the dry periods gradually winning out. But by 3 billion years ago, the transformation was essentially complete. Mars had become the Mars we recognize today: cold, dry, thin-aired, a desert planet with only relics and memories of the water that once flowed. If life emerged during the wet period, it either adapted to the new conditions, going underground, forming spores, finding refuges in subsurface ice, or it went extinct. Either outcome leaves us with profound questions to answer. Some craters on Mars show signs of having been filled with ice-covered lakes as recently as 5 million years ago, maybe even more recently than that. 5 million years is nothing in geological terms. It's yesterday, practically last week. Humans were already evolving in Africa 5 million years ago, and Mars, supposedly a dead, dry world, was apparently still forming ice-covered lakes in certain craters. How is this possible on a planet where liquid water shouldn't be stable? The answer lies in Mars' climate cycles. During periods of high axial tilt, ice at the poles sublimates and redistributes toward lower latitudes. Some of this ice accumulates in craters, especially deep ones that act as cold traps. Over time, you can build up thick deposits of ice. If conditions are right, if the atmosphere thickens slightly due to more ice sublimating elsewhere, if there's volcanic heat or geothermal warmth beneath the ice, you might get melting at the base of these ice deposits. Not a surface lake, but a subglacial lake, hidden beneath meters or kilometers of ice. We have these on Earth. Lake Vostok beneath Antarctica is the most famous, a lake the size of Lake Ontario, buried under 2.5 miles of ice, isolated from the surface for millions of years. If it can happen on Earth, it can happen on Mars. The evidence comes from deposits in these craters that look like they were laid down in water, or from distinctive landforms that suggest ice once filled the crater and then sublimated away, leaving behind collapse features. 5 million years ago is recent enough that these features are still fresh, not heavily cratered or eroded. They're like photographs from Mars's recent past, showing that the planet's climate still shifts, still changes, still creates temporary habitable environments. Maybe it's happening right now, somewhere on Mars, a crater with a thick ice deposit, and beneath that ice, a thin layer of liquid water, too small and too cold for anything we'd call life, but liquid nonetheless. Mars isn't as dead as it seems. It still breathes, still shifts, still surprises us with hints of water, even in its frozen age. On Mars, the sunsets are blue, not the warm oranges and reds we see on Earth, but a soft, cool blue surrounding the sun as it dips below the horizon. The rest of the sky remains that butterscotch tan, but right around the sun itself, there's a gentle blue glow. It's one of the most beautiful inversions. Earth gives us blue skies and red sunsets, while Mars gives us tan skies and blue sunsets. Same physics, opposite results. On Earth, our thick atmosphere scatters short wavelength blue light more than longer wavelength red light. During the day, that scattered blue light comes at us from all directions, making the whole sky appear blue. At sunset, light travels through more atmosphere, scattering away most of the blue and leaving the reds and oranges to paint the horizon. On Mars, the atmosphere is thin, but it's filled with fine dust particles. Iron oxide particles about the same size as the wavelength of visible light. These particles scatter light differently than gas molecules do. They scatter longer wavelength red light more effectively during the day, giving the sky its tan-pink color. But around sunset, when light travels through more dust, The fine particles scatter the blue wavelengths forward, creating that blue glow around the sun. The first color images of a Martian sunset came from the Spirit rover in 2005. Scientists knew theoretically that sunsets should be blue, but seeing it, actually seeing that alien color palette was profound. Imagine standing on Mars as the sun sets. The day's warmth, what little there was, is already radiating back into space. The temperature is dropping rapidly. You can see your breath inside your helmet. The landscape around you is bathed in dusty red light. And there, on the horizon, the sun, smaller than it appears from Earth because Mars is farther out, sinks slowly, surrounded by a halo of blue. It would be beautiful in a way that's hard to describe. Familiar because you've watched thousands of sunsets on Earth. Alien because the colors are inverted, wrong, dreamlike. And then the sun drops below the horizon, and darkness comes quickly. There's no thick atmosphere to hold the light, no long twilight period. Day becomes night in minutes. The stars emerge, sharp and clear in the thin air, and Earth rises, a blue dot among the constellations, reminding you of sunsets that glow red. Every few years, Mars experiences dust storms that grow to cover the entire planet, obscuring the surface for months. These storms start small, local dust devils or regional storms kicked up by seasonal winds. But sometimes, under the right conditions, they grow, and keep growing until they've merged into a single global storm system that wraps around the entire planet. It happened in 2018, and it's what ultimately ended the Opportunity rover's mission. The sky darkened. Solar panels couldn't generate power. Opportunity went into hibernation mode, waiting for the storm to clear. But when the skies finally cleared months later, Opportunity didn't wake up. Too much dust had accumulated on its panels. Its batteries had drained too low. After 15 years of operation, the storm proved too much. From orbit, these global dust storms are spectacular and terrifying. The entire planet turns a uniform tan-orange. Surface features disappear. You can't see Olympus Mons, can't see Valles Marineris. Just dust everywhere, suspended in the atmosphere at all altitudes. But here's what's strange. Despite wind speeds that can reach 60 miles per hour during these storms, you wouldn't feel much if you were standing on the surface. The atmosphere is so thin that even high-speed winds carry very little momentum. It would feel like a gentle breeze, maybe strong enough to slowly push dust around, but nowhere near the destructive forces depicted in The Martian or other science fiction. The danger isn't the wind, it's the darkness. Solar-powered equipment fails. Temperatures drop because sunlight can't reach the surface. Navigation becomes impossible. The entire planet essentially shuts down, waiting for the dust to settle. And eventually, it does. Gravity wins. The dust falls back to the surface, sometimes taking months to fully clear. The sky brightens. The sun reappears. And Mars returns to its normal state. Dusty, yes, but clear enough to see the horizon. These storms are one of the many reasons Mars is challenging. The planet doesn't just sit there passively. It has weather, moods, seasons when it becomes hostile, even by Martian standards. Dust devils on Mars can tower up to 5 miles high, 10 times taller than any tornado on Earth. They're essentially whirlwinds, columns of rotating air made visible by the dust they pick up. On Earth, you see them in deserts and dry fields, spinning faintly in the afternoon heat. On Mars, they're everywhere during the warmer seasons, spinning across plains and crater floors, leaving dark trails where they've swept away lighter colored dust. These trails can be seen from orbit, crisscrossing patterns where dust devils have wandered, dark streaks that fade over time as new dust settles. They're ephemeral graffiti written by wind, erased by wind, rewritten constantly. Because Mars's atmosphere is so thin, these dust devils form easily. There's less atmospheric mass to stabilize, less inertia to overcome. A bit of solar heating creates convection. Air begins to rotate, and suddenly you have a vortex reaching miles into the sky. Rovers have driven through dust devils. The light dims briefly as the column passes overhead. Dust patters against the camera lenses. Sometimes the rover shakes slightly, not from the wind, which is too weak to move it, but from the pressure changes as the vortex passes. And occasionally, dust devils do something useful. They clean solar panels. The Spirit and Opportunity rovers both experienced cleaning events, where dust devils passed over them and blew accumulated dust off their solar panels, increasing power generation and extending their missions by months or years. Imagine watching a Martian dust devil from a safe distance, a towering column of tan dust, spinning slowly, drifting across the landscape like a ghost. Silent because there's too little air to carry sound more than a few feet. 5 miles tall, moving at walking speed, leaving a dark trail in its wake. They form in the morning as the sun heats the ground. By afternoon, there might be dozens visible across a single region. Then, as evening comes and temperatures drop, they dissipate, vanishing as quickly as they formed. Mars is a desert, but it's not still. The air moves, dust rises, and these enormous silent columns dance across ancient plains, stirring up material that's been settling for billions of years. During the daytime, Mars' sky is a butterscotch tan color, not blue like Earth's, but a dusty warm hue that makes everything look slightly sepia-toned. This happens because of iron oxide dust suspended in the atmosphere. The particles are fine, about 1 micron in diameter, roughly the wavelength of visible light, and they hang in the air constantly, even during clear weather. These dust particles scatter red and orange wavelengths more effectively than blue, essentially doing the opposite of what Earth's atmosphere does. Instead of scattering blue light and making the sky blue, they scatter red light, tinting the sky in warm earth tones. The effect is subtle but pervasive. Every photograph taken on Mars has this color cast. The rocks look redder, the shadows look warmer, even the sun appears slightly dimmer, filtered through all that suspended dust. For humans living on Mars, this would become the new normal. You'd stop noticing it after a while, the same way you don't consciously notice Earth's blue sky every moment of every day. But visitors from Earth would find it disconcerting, like living inside an old photograph where everything has aged to warm tones, and the quality of light would be different, softer, more diffuse. Because the dust scatters light in all directions, shadows on Mars aren't as sharp as shadows on Earth. There's more ambient light filling in the dark places, giving everything a slightly flat, even illumination. Photographers would need to adjust. Colors would need to be calibrated differently. Golden hour, that period around sunrise and sunset when Earth's light is warmest and most flattering, would essentially last all day on Mars. Everything bathed in perpetual late afternoon light. It's a small thing, the color of the sky, but it's one of those details that would make Mars feel truly alien. You could get used to the low gravity, the cold, the thin air, but every time you looked up, you'd see a sky that isn't blue, and you'd remember you're not on Earth anymore. Snow falls on Mars, but it's not water snow. It's made of carbon dioxide, dry ice, falling from the sky in tiny flakes. This happens at the poles during winter, when temperatures drop low enough for CO2 to freeze directly out of the atmosphere. It doesn't require clouds or water vapor. The carbon dioxide just reaches its condensation point and crystallizes, forming tiny particles that drift down through the thin air. Most of these flakes sublimate before reaching the ground. The air at lower altitudes is slightly warmer, or the flakes are so small that they evaporate directly from solid to gas before landing. But some make it to the surface, accumulating in layers that add to the seasonal polar caps. Imagine that. Standing on Mars during polar winter, watching snowfall that you couldn't touch without it evaporating. Snow that's colder than any winter storm on Earth, well below 100 degrees. Snow that isn't wet but rather dusty, like sand almost, but cold enough to burn any exposed skin instantly. Water snow exists on Mars too, but it's much rarer. Occasionally, high-altitude clouds form from water ice crystals, and these can produce light snowfall. But it's not the heavy, thick snow that blankets Earth's winter landscapes. It's sparse, scattered, and usually evaporates long before reaching the ground. The carbon dioxide snow, though, that accumulates. Over the course of a Martian winter, the polar ice caps can grow significantly as this dry ice snow piles up layer by layer. Then in spring, it all sublimates back into the atmosphere, and the cycle repeats. It's one more way Mars feels both familiar and alien. Snow is snow, frozen precipitation falling from the sky, but the substance is wrong. The chemistry is different, and the experience of watching it fall would be utterly unlike any winter scene on Earth. White flakes drifting down through a tan sky, disappearing before they hit the ground, or landing and immediately beginning to sublime, releasing tiny puffs of gas. Silent because there's too little air to carry the sound. Cold, colder than you can imagine. Beautiful in its strangeness. At Mars' polar regions, avalanches occur where layers of ice and dust collapse down steep cliffs, tumbling in slow motion through the thin air. These aren't rare events. They happen regularly during spring, when the seasonal dry ice cap sublimates and destabilizes the underlying layers. The Mars Reconnaissance Orbiter has captured several of these avalanches in progress, frozen mid-collapse by its high-resolution camera. The images are striking. A cliff edge, stark white with ice, and then a massive plume of material. Ice chunks, dust, vapor, cascading down, spreading out into a cloud that reaches hundreds of feet into the air before settling. Because of the low gravity, these avalanches fall slowly compared to Earth equivalents. Material that would plummet rapidly on Earth drifts almost lazily on Mars, giving the collapse a strange, dreamlike quality. And because the atmosphere is so thin, there's no air resistance to slow the debris. Chunks of ice can bounce and tumble for extraordinary distances before finally coming to rest. The cliffs themselves are layered, alternating bands of ice and dust that record climate cycles going back millions of years. Each layer is a time marker, light layers representing periods when clean ice accumulated, dark layers showing dustier periods when storms were more common. When an avalanche happens, it exposes fresh, clean ice that hasn't seen sunlight in millennia. The newly exposed face is brighter, almost gleaming compared to the dust-covered surroundings. But within days or weeks, dust begins to settle on it, darkening it again. These avalanches are part of how Mars' poles erode and evolve. The ice isn't static. It's constantly being redeposited, consolidated, and removed. The polar layered deposits are archives, but they're living archives, still being written and occasionally edited by collapse and sublimation. If humans ever establish bases near the poles, to mine water ice perhaps, these avalanches would be a constant hazard. You'd need to monitor the cliffs, watch for signs of instability, stay clear during spring when sublimation makes collapses most likely. But they'd also be beautiful, terrifying certainly, but beautiful in the way natural disasters often are, raw displays of geological forces, playing out in slow motion under a butterscotch sky. On Mars, water can't remain liquid. The atmospheric pressure is so low that water either freezes solid or immediately boils away. There's no stable liquid phase at typical Martian surface conditions. This is deeply strange. Water is so fundamental to our understanding of habitability. We think of it as a substance with three phases: ice, liquid, vapor. But on Mars, liquid water, the phase we care about most for biology, is essentially forbidden. The physics is straightforward. Liquids exist when the temperature and pressure fall within a specific range. On Earth, water is liquid between 32 degrees and 212 degrees at sea level pressure. But if you lower the pressure, you also lower the boiling point. At Martian pressures, water boils at temperatures barely above freezing. So if you took a glass of liquid water to Mars and set it outside, several things would happen almost simultaneously. Part of it would start to freeze because Mars is cold, but part would also start to boil, even though it's cold, because the pressure is so low. The boiling would cool the water further through evaporative cooling, freezing it faster. Within seconds, you'd be left with a chunk of ice surrounded by water vapor that quickly disperses into the thin air. It's called the triple point, the specific pressure and temperature where all three phases coexist. Mars sits right near that boundary, which is why water is so unstable there. But here's the loophole: salty water, brines. When you dissolve salts in water, you change its freezing and boiling points. A concentrated brine can remain liquid at lower temperatures and pressures than pure water. This is why scientists get excited about perchlorates in Martian soil. These salts could potentially allow liquid water to exist in thin films or small pockets, at least temporarily. It wouldn't be pleasant water. It would be extremely salty, cold enough to freeze unprotected skin instantly, and probably toxic. But it would be liquid. And where there's liquid water, there's at least a theoretical possibility for chemistry to happen. Still, the fact remains: Mars is a world where one of the universe's most common molecules can't easily exist in its most useful form. Water is there, frozen in the ground, locked in the poles, trapped in minerals. But flowing, pooling, life-sustaining liquid water, that belongs to Mars' past, not its present. Mars experiences temperature swings of 100 degrees Fahrenheit or more between day and night, a fluctuation that would be unthinkable on Earth outside of extreme desert environments. You could experience summer afternoon temperatures near the equator, maybe 70 degrees at ground level, warm enough to technically be comfortable if it weren't for the vacuum-like atmosphere and deadly radiation. Then that same night, in that same spot, temperatures plummet to 100 degrees or colder. This wild swing happens because Mars has almost no thermal mass in its atmosphere. On Earth, air holds heat. Water vapor especially acts as a greenhouse gas, trapping infrared radiation and moderating temperature changes. Our oceans also help, massive bodies of water that absorb heat during the day and release it slowly at night. Mars has none of this. The atmosphere is thin and dry. There are no oceans. When the sun shines on the ground, it heats up quickly. But that heat doesn't spread or get absorbed by anything substantial. And the moment the sun sets, that heat radiates directly back into space. No atmosphere to hold it in, no water to store it, just immediate, brutal cooling. For habitats on Mars, this means you'd need incredible insulation. Your shelter would need to hold heat through the night without external power if possible, and shed excess heat during the day. Airlocks would be thermal bottlenecks. Every time you open them, you'd be letting in extreme temperatures, either hot or cold, depending on the time of day. Spacesuits would need sophisticated thermal control systems, heating for night, cooling for day. The human body generates heat through metabolism, and in a well-insulated suit during daylight, you could actually overheat even though the external temperature is below freezing. But there's something almost poetic about these extreme swings. Mars doesn't hold on to anything. Not heat, not water, not atmosphere. Everything that arrives leaves again quickly. The planet exists in a state of constant flux, unable to maintain equilibrium, always swinging between extremes. It's a harsh way to live, but it's Mars' way. And anyone who lives there will need to adapt to a world that changes temperature more in 12 hours than most places on Earth change in an entire season. The Borealis Basin is an enormous geological feature covering about 40% of Mars's northern hemisphere, and it might be one of the largest impact craters in the solar system. Might be, because that's still debated. The basin is huge, roughly 6,600 miles across and several miles deep. If it's an impact crater, the asteroid that created it would have been larger than Pluto. The collision would have been one of the most violent events in the history of the solar system, enough to partially melt Mars' crust, create a temporary atmosphere of vaporized rock, and fundamentally reshape the planet's geology. Some scientists argue that the basin's elliptical shape and the magnetic anomalies around its rim support the impact hypothesis. Others suggest it might be a natural feature created by plate tectonics or mantle convection in Mars's early history, a massive low point that formed as the planet cooled and contracted. The truth is, we don't know for certain. The features that would definitively prove an impact, like shocked minerals or a distinctive crater rim, have been eroded or obscured by billions of years of geological activity. But if it is an impact crater, the implications are staggering. The collision would have occurred over 4 billion years ago, during the late heavy bombardment, when asteroids and comets pummeled the inner solar system. Mars, being smaller and with weaker gravity than Earth, would have taken proportionally more damaging hits. This impact could have stripped away much of Mars's early atmosphere. It might have disrupted the planet's magnetic field by shocking the core. It could have created so much heat that the entire northern hemisphere became a temporary magma ocean. In other words, this single event, if it happened, might explain why Mars is the way it is today, why it lost its magnetic field, why its atmosphere is thin, why the northern and southern hemispheres are so different. One collision, 4 billion years ago, reshaping the destiny of an entire world. Or maybe it's not an impact crater at all. Maybe it's just a basin, formed by more mundane geological processes. But the uncertainty itself is fascinating. We're looking at a feature that covers nearly half a planet, and we still can't agree on how it formed. Mars keeps its secrets. Occasionally, Mars has meteors that are made of Martian material, re-entering its own atmosphere after being blasted into space by asteroid impacts. Think about the journey these rocks take. An asteroid slams into Mars, excavating a crater and launching debris into space. Some fragments escape Mars entirely and wander the solar system, but others are flung into elliptical orbits that still intersect with Mars. They circle the sun for a while, maybe thousands of years, maybe millions, and then their orbit decays or shifts slightly, and they fall back toward Mars. They re-enter the Martian atmosphere, burning as meteors, shooting stars made of Mars falling back home. It's a cosmic recycling program. Rock leaves Mars, orbits for eons, and returns. Some of these returning fragments might even land near their original impact site, having traveled millions of miles only to end up close to where they started. We know this happens because the math works out. Orbital mechanics predicts it. But we've never directly observed a Martian meteor that we could confirm was Martian in origin. They'd look just like any other meteor, just another bright streak in the night sky. But imagine being one of the first humans on Mars, standing outside in the evening, watching the stars, and you see a meteor streak overhead, a shooting star, just like on Earth. Except this one might be a piece of Mars itself, coming home. There's something poetic about that. Mars launching fragments of itself into space, those fragments wandering for ages, and then gravity reaching out and pulling them back. The planet reclaiming its lost pieces. It's also a reminder that planetary surfaces aren't permanent. Material is constantly being exchanged between planets and space, between the surface and the interior, between solid and vapor. Nothing stays put forever. Everything circulates eventually. Even the rocks beneath your feet might have, billions of years ago, been launched into space and fallen back. Travelers who left and returned, carrying stories written in microscopic crystal structures. Stories we're only just beginning to learn how to read. Phobos, the larger of Mars' two moons, rises in the west and sets in the east, the opposite of almost every other natural satellite in the solar system. This happens because Phobos orbits Mars so quickly. It completes one full orbit in just 7 hours and 39 minutes, faster than Mars rotates. So from the surface, Phobos appears to move backwards across the sky, racing from western horizon to eastern horizon in about 4.5 hours. It's disorienting to think about. On Earth, we're used to celestial objects rising in the east. The sun, the moon, the stars. It's one of those fundamental orientations that shapes how we think about sky and time. But on Mars, Phobos breaks that rule. And it doesn't just rise once per day. It rises and sets more than twice in a single Martian day. You could watch Phobos set in the east, wait a few hours, and watch it rise again in the west. Then set in the east again, an accelerated lunar cycle playing out overhead. Deimos, the smaller, more distant moon, behaves more normally. It rises in the east and sets in the west, taking about 2.7 days to complete that journey. But even Deimos moves faster than Mars's rotation would suggest, creating a strange sky where one moon rushes backward and the other crawls forward. For colonists, this would become a familiar rhythm, Phobos chasing itself across the sky, Deimos drifting slowly in the opposite direction. Occasionally, they'd pass each other, creating brief double moon moments. There would be no month as we know it, no lunar calendar based on moon phases, because Phobos and Deimos are too small and dark to go through dramatic phases like Earth's moon does. They'd appear as tiny points of light, moving at odd speeds, reminding anyone watching that they're living under different rules now. Imagine lying on the Martian surface at night, looking up. The stars are steady, recognizable. Earth is visible as a blue dot, but Phobos is racing overhead, moving visibly if you watch for just a few minutes, heading the wrong direction. It would feel like the universe was broken, just slightly, like physics was running backwards in one small way. But it's not broken. It's just Mars, where even the moons refuse to follow the patterns we expect. Phobos is spiraling inward toward Mars, and in about 50 million years, maybe less, it will either crash into the planet or be torn apart by tidal forces, creating a temporary ring system. This is gravity's inevitable mathematics. Phobos orbits so close to Mars that tidal forces, the difference in gravitational pull on the near and far sides of the moon, are slowly sapping its orbital energy. With each orbit, it drops a little closer, about 6 feet per century, which doesn't sound like much until you multiply it by enough centuries. Eventually, Phobos will cross what's called the Roche limit, the distance at which tidal forces overcome the moon's own gravity. At that point, Phobos will begin to fracture. Cracks will spread. Pieces will break off. The moon will stretch and deform, pulled apart not by a single catastrophic event, but by the patient, inexorable tug of Mars's gravity. Those fragments will spread out along Phobos's orbital path, creating a ring around Mars, possibly a spectacular one, visible from the surface as a bright band arching across the sky. The rings might last for tens of millions of years before the particles gradually spiral down and impact the surface, or Phobos might hold together long enough to actually impact Mars as a single body. If that happens, it would create a crater about 100 miles across, significant but not catastrophic. The impact wouldn't threaten the planet's geology in any fundamental way. Just add one more scar to a surface already covered in ancient craters. Either way, Phobos's days are numbered. It's a temporary feature, a moon with an expiration date. In the grand timeline of the solar system, it won't be there much longer, and there's something melancholic about that. This small, potato-shaped moon, Fear itself, named after the companion of war, is falling, has been falling for its entire existence. Every time it crosses the Martian sky, it's a little closer to its end, but for now it remains. Rising in the west, setting in the east, racing around its planet 3 times a day. A doomed moon, still orbiting, still visible to anyone who looks up, present but temporary, like everything else in the universe, really, just moving faster toward its conclusion than most. During Martian winter, up to 25% of the entire atmosphere freezes out of the air and deposits at the poles as dry ice. 25%. A quarter of all the air on the planet simply condenses, becomes solid, falls out of the sky as carbon dioxide snow and accumulates at the poles in thick layers. This means the atmospheric pressure across the entire planet drops measurably during winter. If you had a barometer on Mars, you'd see the pressure decline as winter approaches, then rise again in spring as that frozen CO2 sublimates back into the atmosphere. The planet breathes, literally, inhaling atmosphere in winter, exhaling it in summer. A slow, seasonal respiration cycle that takes most of a Martian year to complete. On Earth, our atmosphere is stable. Yes, there are pressure systems and weather fronts, but the total amount of atmosphere doesn't change significantly. The air that's here stays here, but Mars' atmosphere is marginal enough, thin enough, that significant portions of it can phase change between solid and gas with the seasons. It's as if Mars can't quite hold on to being a planet with an atmosphere. It's right on the edge, and depending on the season, it tips toward having more air or less air, constantly balancing on that knife edge between atmosphere and vacuum. This breathing has consequences. The winds that drive dust storms are partly powered by CO2 condensing at one pole and sublimating at the other, creating pressure differences that drive air movement. The entire atmospheric circulation of Mars is shaped by this seasonal freezing and thawing, and for future colonists, this would be one more variable to track. Atmospheric pressure isn't constant on Mars. It varies with season and location. Your habitat's pressure differential with the outside would change throughout the year. Life support systems would need to account for this. But there's also something almost alive about it. Mars breathing, taking in air when it's cold, releasing it when it warms. A planetary metabolism, slow and cold but persistent. The whole world inhaling and exhaling in a rhythm that's been maintained for billions of years. Near the Martian South Pole, strange formations called spiders appear. Radial channels carved into the surface that branch out from central points like legs. They're not alive, of course, they're erosion features. But their formation process is genuinely alien, something that doesn't happen on Earth. Here's how they form. During southern spring, sunlight penetrates the translucent layer of dry ice, frozen CO2, that accumulated over winter. The light reaches the dark ground beneath and warms it. That warmth causes the CO2 ice at the bottom of the layer to sublimate, to go directly from solid to gas. But this gas is trapped beneath the remaining ice layer. Pressure builds. Eventually, the gas breaks through, erupting like a geyser, carrying dark sand and dust from the ground up through the ice. This material gets deposited on the surface, creating dark spots and streaks. Over time, as this process repeats in the same locations year after year, it carves channels into the ground, radial patterns that spread out from weak points in the ice, creating these spider-like formations. Some of them have dozens of legs radiating from a central point. They can be hundreds of feet across. From orbit, regions with these spiders look like they're covered in strange, organic patterns. Dark branching structures against the lighter ice. They appear in spring, fade over summer as new dust settles, and then reappear the next spring in the same locations. It's a formation process that's unique to Mars, or at least unique to places with seasonal CO2 ice and dark underlying material. The combination of sublimation pressure, ice transparency, and surface composition creates these features that look almost biological, but are purely geological. Imagine being there in spring, watching the surface come alive. Dark geysers erupting from the ice, carrying dust high into the thin air. The hiss of escaping carbon dioxide, though you couldn't hear it. There's not enough air to carry sound. Patterns emerging across the landscape as these eruptions etch their marks. The spiders would be temporary features, visible only in certain seasons, but they'd return every year, predictable as clockwork. Mars' way of decorating its polar regions, creating art through physics. Mars has caves formed by ancient lava tubes, hollow channels where molten rock once flowed, now empty and potentially stable enough to shelter future astronauts. Lava tubes form when the surface of a lava flow cools and solidifies, while molten lava continues to flow beneath, eventually draining away and leaving a hollow tunnel. On Earth, these tubes can be quite large. Some in Hawaii and Iceland are big enough to drive buses through. On Mars, with its lower gravity, lava tubes could be even larger. The reduced gravitational stress means the roof of a tube can span greater distances without collapsing. Some models suggest Martian lava tubes could be hundreds of feet wide and miles long. We've identified several likely lava tube entrances, skylights where the roof has partially collapsed, creating openings to the dark spaces beneath. Orbital images show these as dark spots with no apparent bottom, surrounded by the characteristic sinuous channels that suggest old lava flows. These tubes are exciting for multiple reasons. First, they're natural shelter, protection from radiation, from temperature extremes, from dust storms. The interior of a lava tube would maintain a relatively stable temperature, shielded from the dramatic day-night swings that occur on the surface. Second, they might preserve ice. In the darkness and cold of a deep cave, water ice could exist even at equatorial latitudes where surface ice would quickly sublimate. A lava tube could be a water source in regions otherwise too warm to have accessible ice. Third, and perhaps most intriguingly, they could harbor life. If microbial life exists on Mars today, it's probably underground, protected from radiation and temperature extremes. Lava tubes would be ideal refuges, stable environments where liquid water might occasionally exist, where organic chemistry could proceed, protected from harsh surface conditions. No mission has yet entered a Martian lava tube. We've only seen them from above, through the skylights. But they're on the list for future exploration. Imagine sending a rover to the edge of one of these dark openings, shining lights into the depths, seeing the smooth walls disappear into shadow. Or imagine humans establishing a base in one. Natural radiation shielding, stable temperatures, vast interior spaces that could be pressurized, lit, transformed into underground habitats. Mars's own geology providing shelter for the species trying to colonize it. The caves are waiting, dark, silent, preserved exactly as they were when the last lava drained away billions of years ago, ready to be explored. In 1976, one of the Viking orbiters photographed what appeared to be a face in the Cydonia region, a mesa that, in low-resolution imagery and specific lighting, looked remarkably like a humanoid face staring up from the Martian surface. It became one of the most famous images from Mars. Books were written about it. Theories proliferated. Some suggested it was an artificial structure, evidence of ancient Martian civilization. The idea captured public imagination in a way few scientific images ever have. But here's the thing about the human brain. We're pattern recognition machines. We evolved to spot faces in shadows, in foliage, in random arrangements of features. It's called pareidolia, and it kept our ancestors alive by helping them quickly identify friend, foe, or predator. So when we see two dark spots above a line in a roughly triangular arrangement, our brains say face, even when it's just rocks and shadows. Later missions returned to Cydonia with better cameras. The Mars Reconnaissance Orbiter, with resolution sharp enough to see individual boulders, photographed the face in detail, from multiple angles, in different lighting conditions. And it's just a mesa, an eroded hill. The eyes are shadows in depressions. The nose is a ridge. The mouth is another shadow. From different angles, it doesn't look like a face at all. It looks like a weathered rock formation, which is exactly what it is. But the episode is valuable. Not because it revealed alien civilizations, it didn't, but because it revealed something about us, about how eager we are to find meaning, patterns, evidence of other minds, about how our psychology shapes what we see. Mars is covered in rocks, billions of rocks in countless shapes and arrangements. Some of them, purely by chance, will look like faces, or animals, or letters, or anything else our pattern-seeking brains want to see. The face on Mars is a reminder to be skeptical, to demand better evidence, to recognize that what we see isn't always what's there. But it's also a reminder of how much we want Mars to be more than just rocks and dust, how much we want to find evidence that we're not alone, that intelligence has arisen elsewhere, that the universe contains minds other than our own. The face isn't a face, but our desire to see faces on Mars. That's real. That's human. And that desire will drive us to keep exploring, keep searching, keep hoping that somewhere in the rocks and ice we'll find something that looks back. Mars's polar caps contain layered deposits that work like tree rings, recording millions of years of climate history in frozen archives. These layers are visible in cross-section where cliffs or scarps expose the interior structure of the polar ice. Light layers, dark layers, each one representing a different climate period, a different balance of ice accumulation and dust deposition. The light layers are relatively pure ice, times when less dust was being deposited, when the atmosphere was clearer. The dark layers contain more dust, evidence of dustier periods, more storms, different atmospheric circulation patterns. By counting and measuring these layers, scientists can reconstruct Mars' climate history going back millions of years. They can identify cycles, periodic variations driven by changes in Mars's orbital parameters and axial tilt. They can track when the climate was relatively stable versus when it was chaotic. Some of these cycles match predictions from orbital mechanics. Mars's obliquity, axial tilt, wobbles on roughly 120,000-year cycles. Its orbital eccentricity varies on even longer timescales. These astronomical changes affect how much sunlight reaches different parts of Mars at different times, driving climate variations that get recorded in the ice. It's similar to ice cores from Earth's Antarctica and Greenland, which preserve records of our planet's climate going back hundreds of thousands of years. But Mars polar deposits potentially go back much, much further, potentially tens of millions of years or more. Drilling into these deposits would be one of the most scientifically valuable things we could do on Mars. Each layer would tell us about atmospheric pressure, dust storm frequency, the presence of volcanic gases, maybe even hints about biological activity if any existed. But they'd also tell us about cycles, how Mars' climate shifts and changes even in its current frozen state. Because Mars isn't static. It never has been. It's a planet that oscillates between different cold states, sometimes slightly less cold, sometimes even colder, driven by the complex dance of its orbit and rotation. The poles are libraries, frozen books with millions of pages, and we've barely begun to read them. Martian soil contains chemicals called perchlorates, salts that are toxic to humans but might actually be one of the reasons liquid water can occasionally exist on Mars. Perchlorates are chlorine-based compounds that have some interesting properties. They're hygroscopic, meaning they attract water from the atmosphere. They lower the freezing point of water significantly, and they lower the pressure at which water can remain liquid. On Earth, perchlorates are relatively rare and are usually associated with desert regions or industrial contamination. On Mars, they're widespread. The Phoenix lander detected them in polar soil. Curiosity found them in equatorial regions. They seem to be a common component of Martian surface chemistry. This is both bad news and good news for future Mars missions. Bad news: perchlorates are toxic. They interfere with thyroid function in humans. They'd need to be removed from any soil used for growing food. Spacesuits and equipment that contact Martian soil would need careful decontamination. You couldn't just track Martian dust into a habitat and ignore it. Good news: perchlorates could be part of what allows those mysterious recurring slope lineae to exist. A concentrated brine solution of perchlorate salts can remain liquid at temperatures well below the freezing point of pure water and at pressures much lower than Earth's atmosphere. Even better news: perchlorates contain oxygen, a lot of it. They could potentially be used to manufacture oxygen for breathing or rocket fuel. The same toxic chemical that's a contamination hazard could also be a valuable resource. It's typical Mars. Nothing is straightforward. Every discovery has multiple implications, some helpful, some hazardous. The planet gives with one hand and takes with the other. But the presence of perchlorates is one more piece of evidence that Mars's chemistry is more complex than a simple dead rock in space. Active chemistry is happening. Water and salts interact. Temporary conditions allow phases and mixtures that shouldn't be stable but briefly exist anyway. Mars is right at the edge of habitability. Not quite habitable, but close enough that with a little help from chemistry, from salts and brines, and temporary thermal fluctuations, liquid water can maybe, sometimes, briefly exist. Not easy, not abundant, but possible, just barely possible. Over 50 missions have been sent to Mars since the space age began, but only about half have been successful. Mars has earned a grim reputation as the Bermuda Triangle of space, or the death planet. Orbiters lose contact, landers crash, entry, descent, and landing sequences fail in bewildering ways. Part of this is just the difficulty of space travel in general. Getting to Mars requires a launch window that only opens every 26 months. The journey takes 6 to 9 months. If anything goes wrong during that time, there's no way to send help. Once you commit, you're committed. The entry, descent, and landing sequence, 7 minutes of terror, as NASA engineers call it, is particularly challenging. You hit Mars' atmosphere at around 12,000 miles per hour. You need to slow down to zero in a matter of minutes, using a combination of heat shields, parachutes, and retro rockets. The atmosphere is thick enough to create intense heating, but too thin to really break your spacecraft effectively with parachutes alone. You're in this awkward middle zone where you need multiple systems working in perfect sequence, and if any one thing fails, the entire mission fails. The Soviet Union had particularly bad luck with Mars. They sent numerous missions in the 1960s and 70s, and nearly all of them failed. Some before even leaving Earth orbit, others during the cruise to Mars, others during landing. Mars 3 successfully landed in 1971, but transmitted for only 14.5 seconds before going silent. Even NASA has had failures. Mars Observer in 1992, Mars Climate Orbiter in 1999, lost due to a unit conversion error between metric and imperial. Mars Polar Lander the same year, but the successes, Viking, Pathfinder, Spirit, Opportunity, Curiosity, Perseverance, and numerous orbiters, have been spectacular. Each successful mission returns orders of magnitude more data than its predecessors. Our understanding of Mars has exploded over the past few decades. Still, Mars demands respect. It's not easy to reach, not easy to land on, not easy to survive on. The planet is challenging every step of the way, as if testing whether we're serious about exploring it, proving that we need to earn whatever knowledge we extract. Half our missions fail, but the other half succeed, and those successes are worth the attempts. The first successful Mars rover was named Sojourner, and it was tiny, about the size of a microwave oven, weighing just 23 pounds. It landed in July 1997 as part of the Mars Pathfinder mission, and it was only designed to last for 7 days. 7 days to prove that a rover could work on Mars, could drive around, could analyze rocks, could operate autonomously. It lasted 85 days, 12 times longer than planned, and in that time, it traveled about 330 feet. Not far. You could walk that distance in a minute on Earth, but on Mars, that 330 feet was groundbreaking. Sojourner had 6 wheels, each independently controlled and motorized. It could climb over rocks twice its wheel height. It moved at a top speed of about 0.02 miles per hour, roughly a centimeter per second. Slower than a snail, but reliable. It carried an alpha proton X-ray spectrometer that could analyze the chemical composition of rocks and soil. It had cameras. It had solar panels and a battery system. In many ways, it was the prototype for all the rovers that would follow. And it captured public imagination in a way few scientific missions ever have. People logged onto NASA's website to see the latest images, crashing the servers with traffic. The idea of a tiny robot trundling across Mars, picking its way around rocks, beaming back pictures, it made Mars feel accessible, knowable, almost friendly. Sojourner was named after Sojourner Truth, the African-American abolitionist and women's rights activist. A rover named for someone who traveled and spoke truth, now traveling on Mars and sending back truths about another world. Eventually, the Pathfinder lander's battery failed, and contact was lost. Sojourner probably tried to maintain communication for a while, moving back to the lander periodically to check for signals. Then its own batteries died, and it stopped. It's still there, somewhere in Ares Vallis, covered in dust by now, silent. But it proved that rovers could work, that we could send mobile robots to Mars and have them explore far beyond a single landing site. Sojourner was tiny, but it opened the door, and through that door came Spirit, Opportunity, Curiosity, Perseverance, each one larger, more capable, more ambitious, all of them descendants of that first small rover that proved it could be done. The Spirit and Opportunity rovers were twins, identical in design, launched to Mars in 2003 and landing in January 2004. They were designed to last 90 days. Spirit operated for 6 years, Opportunity for 15 years, on a mission designed for 3 months. They were golf cart sized, weighing about 400 pounds each, solar-powered, 6 wheels, a robotic arm with instruments for analyzing rocks, cameras that could capture panoramic views in true color, and enough autonomy to navigate around obstacles without waiting for instructions from Earth. Spirit landed in Gusev Crater, which scientists thought might be an ancient lake bed. Opportunity landed on the other side of the planet in Meridiani Planum, where orbital spectrometers had detected hematite, a mineral that often forms in water. Both rovers exceeded every expectation. Spirit climbed hills, analyzed rocks, discovered evidence of past water, and survived dust storms and cold Martian winters. Eventually, one of its wheels stopped working, and it had to drive backwards, dragging the broken wheel. That broken wheel actually proved useful. It dug a trench that exposed bright subsurface material that turned out to be nearly pure silica, evidence of ancient hot springs or steam vents. Spirit finally got stuck in soft soil in 2009. Engineers tried for months to free it, but it was trapped. As winter approached and solar power dwindled, Spirit went silent. It's still there, tilted at an angle in a place now called Troy, its solar panels likely covered with dust. Opportunity kept going. It drove 28 miles across Martian terrain, a marathon distance, on another planet, with a robot that was supposed to last 90 days. It found blueberries, small spherical concretions of hematite that formed in water. It examined crater walls. It survived dust devils that actually cleaned its solar panels, giving it power boosts when it needed them most. In 2018, a global dust storm engulfed Mars. The sky darkened. Opportunity's solar panels couldn't generate power. It sent a final transmission, essentially a message saying its batteries were low and it was entering hibernation, and then went silent. When the storm cleared months later, NASA spent months trying to contact Opportunity, sending wake-up commands, listening for any response, but the rover never woke up. Too much dust had accumulated, the batteries had drained too far, or some component had failed in the cold. NASA officially declared the mission complete in February 2019, 15 years after landing. There's something profoundly moving about these rovers. They were robots, yes, machines, but they had personalities, quirks. They survived challenges that should have destroyed them. They kept working, kept exploring, kept sending back data years after they were supposed to stop. And when Opportunity died, people mourned. Scientists who had worked with it for 15 years, engineers who had guided it across Mars, people around the world who had followed its journey. There were obituaries, tributes. XKCD published a comic showing Opportunity's last thoughts. "My battery is low and it's getting dark." That made people cry. We send robots to Mars, and somehow they become more than robots. They become emissaries, pioneers, small, brave things venturing into the unknown on our behalf. Spirit and Opportunity transformed our understanding of Mars. They proved that water had shaped the landscape. They showed us ancient environments that could have supported life. They demonstrated that rovers could work far beyond their design lifetimes if built well and operated carefully. And they showed us that humans can form emotional connections to machines exploring other worlds, that we can care about robots dying alone on distant planets. That exploration isn't just about data. It's about the courage to go, the persistence to keep going, and the bittersweet knowledge that all journeys eventually end. The Curiosity rover, which landed on Mars in 2012, is powered by a radioisotope thermoelectric generator, essentially a nuclear battery fueled by the radioactive decay of plutonium-238. Unlike Spirit and Opportunity, which relied on solar panels, Curiosity carries its own miniature power plant. About 10.6 pounds of plutonium-238 oxide, housed in a heavily shielded container, generates heat through radioactive decay. That heat is converted to electricity using thermocouples, about 110 watts of electrical power at the start of the mission. This was a crucial design choice. Curiosity is much larger than previous rovers, about the size of a small car, weighing nearly 2,000 pounds. Solar panels large enough to power it would be impractically huge and fragile. And unlike Spirit and Opportunity's equatorial landing sites, Curiosity landed at higher latitude where winter sunlight is weaker. But nuclear power provides other advantages. It works day and night. It works during dust storms. It produces waste heat that keeps electronics warm during cold Martian nights, reducing the energy needed for heaters. It's predictable. The power output decreases slowly, steadily, as the plutonium decays. But that decline is well understood and happens over decades. The plutonium-238 has a half-life of 87.7 years, meaning Curiosity's power source could theoretically keep it running for decades. The rover won't die from lack of power. It'll die when mechanical systems wear out, when actuators fail, when too much dust accumulates on critical sensors. This nuclear power is why Curiosity could carry heavier, more sophisticated instruments. The sample analysis at Mars, SAM-Suite, which can heat rock samples to high temperatures and analyze the gases released. The ChemCam laser, which can vaporize rock targets from a distance. The drill, which can bore into solid rock and collect samples from the interior. Perseverance, the newest rover, uses the same power system. A multi-mission radioisotope thermoelectric generator, MMRTG, based on the same plutonium-238 fuel. This gives both rovers the endurance needed for long-term missions, the flexibility to work in any season or weather, and the power budget for sophisticated science. There's something poetic about using nuclear decay. The transformation of atoms from one element to another, releasing energy in the process, to power exploration of another planet. The same physics that makes radioactive elements unstable is what keeps Curiosity alive. Entropy, carefully harnessed and converted to work. Curiosity has now been operating for over a decade, far beyond its initial 2-year primary mission. It's climbed Mount Sharp, analyzed hundreds of rock samples, discovered organic molecules, measured radiation levels, and fundamentally changed our understanding of Mars' habitability. And it could keep going for years more. Not forever, nothing lasts forever, but long enough to climb higher, see farther, and send back discoveries we haven't imagined yet. The plutonium keeps decaying, the heat keeps flowing, the wheels keep turning, and Curiosity keeps exploring, powered by the patient transformation of atoms into energy, one decay at a time. In April 2021, a small helicopter named Ingenuity became the first aircraft to achieve powered, controlled flight on another planet. Think about what that required. Mars's atmosphere is about 1% as dense as Earth's. That's roughly equivalent to flying at 100,000 feet altitude on Earth, 3 times higher than commercial jets fly, well into the realm of near space. To generate lift in such thin air, Ingenuity's rotor blades spin at 2,400 RPM, about 5 times faster than a typical Earth helicopter. The entire aircraft weighs just 4 pounds. It's mostly carbon fiber and aluminum, with solar panels for charging and a battery for flight power. The engineering challenges were immense. The rotors needed to be light but strong, capable of withstanding enormous centrifugal forces without breaking. The flight control software needed to operate autonomously. Radio signals take minutes to travel between Earth and Mars, so there's no possibility of remote piloting. Ingenuity receives flight plans from Earth, then executes them on its own, making split-second adjustments to maintain stability. And it needed to survive Martian nights when temperatures drop to 130 degrees or colder. Its battery and electronics are kept warm by a small heater, but that drains power. Every morning is a race. Wake up, warm up critical components, charge batteries from sunlight, fly, land, survive the night, repeat. Ingenuity was designed for 5 test flights over 30 days, a technology demonstration, proof that flight is possible on Mars. If it worked, great. If it crashed, well, it was a bonus experiment attached to Perseverance's mission. It didn't crash. It flew 5 times successfully. Then NASA extended the mission. Ingenuity kept flying, 10 flights, 20, 30, 50. By early 2024, it had completed over 70 flights, covering several miles of Martian terrain, scouting routes for Perseverance, exploring areas the rover couldn't reach. Eventually, on its 72nd flight in January 2024, Ingenuity damaged its rotor blades during landing and could no longer fly. But it had wildly exceeded its design life, proving that aerial exploration of Mars isn't just possible, it's practical. Future Mars missions will likely include helicopters or drones, maybe larger ones, capable of carrying small payloads, maybe fleets of them, exploring multiple sites simultaneously, maybe even crewed aircraft someday, though that's far in the future. But Ingenuity was first, a tiny helicopter, weighing less than a house cat, proving that humans can build machines that fly on Mars. That thin air and low gravity aren't insurmountable obstacles. That the sky above Mars is accessible, not just to orbiting spacecraft, but to vehicles that can hover, maneuver, land, and take off again. There's footage of Ingenuity flying, taken by Perseverance's cameras, grainy, distant, but unmistakable, rotor blades spinning into a blur, the small craft lifting off the surface, hovering, translating sideways, landing. Each movement a small miracle of engineering. And in those few seconds of video, you can see the future, not just of Mars exploration, but of how humans will move through alien environments. On the ground, yes, but also through the air, skimming over valleys, hovering at cliff edges, landing on peaks that rovers can't reach. Ingenuity flew, and in doing so, it opened the skies. Ingenuity was designed for 5 flights. It completed 72, each one a risk, each one pushing components beyond their design limits, each one another chance for something to go wrong, a motor failure, a software glitch, a hard landing, a dust storm. But it kept flying, through seasonal changes, through temperature extremes, through dust devils and wind gusts. It became not just a technology demonstration, but an operational asset, scouting terrain ahead of Perseverance, exploring scientifically interesting sites, testing the limits of what aerial vehicles can do on Mars. Some of its flights were short hops, just a few seconds of airtime, moving a few feet. Others were long excursions, covering hundreds of meters, staying aloft for 2 or 3 minutes. Each flight required careful planning. Engineers would analyze terrain, check weather models, assess battery levels, and upload flight parameters. Then Ingenuity would wake up, spin up its rotors, and fly completely autonomously, executing the uploaded commands while monitoring its own systems for problems. And every time it landed successfully, engineers would exhale. Another flight complete, data downloaded, battery still charging, heaters still working, ready for the next flight. The end, when it came, was relatively gentle. On Flight 72, during landing, Ingenuity encountered unexpected terrain, possibly a bland, featureless patch of sand that gave its navigation system insufficient visual cues. It touched down harder than intended, damaging at least one rotor blade. Post-flight images showed the damage clearly. One blade with a visible chunk missing. Not catastrophic. Ingenuity could still spin its rotors, but enough to create imbalance that would make controlled flight impossible. So it stopped flying, not destroyed, not lost to communication failure, just grounded, sitting on the Martian surface, still powered, still sending data, still communicating, but unable to fly. In a way, it's a dignified ending. Ingenuity pushed its limits for nearly 3 years, flew almost 15 times farther than planned, and then gracefully retired when its hardware finally gave out. It's still there, in a place that'll probably be named after it someday. The first aircraft to fly on another planet, now a permanent monument to what it achieved. And the data it collected, the lessons learned about flying in Martian conditions, will inform every future aerial vehicle sent to Mars. Ingenuity didn't just prove that flight was possible. It showed how to do it reliably, repeatedly, in conditions that should have grounded it dozens of times. 72 flights, nearly 3 years, millions of rotor rotations, all in atmosphere so thin it barely deserves the name. A small helicopter that could, and did, again and again and again. The Perseverance rover is collecting rock samples that will, if everything goes according to plan, be returned to Earth by a future mission, the first samples ever brought back from Mars. This is more complicated than it sounds. Perseverance drills into rocks, extracts cores about the size of a piece of chalk, seals them in ultra-clean metal tubes, and stores them. So far, it's collected over 20 samples from various locations in Jezero Crater. But getting them back to Earth requires an entire campaign involving multiple spacecraft and launches. A Mars sample return mission would need to land a small rocket on Mars near Perseverance, have Perseverance deliver its samples to that rocket, or send a small fetch rover to collect them, launch the samples from Mars into orbit, the first rocket launch from another planet, have an orbiter rendezvous with those samples in Mars, orbit capture the samples, and place them in a secure containment system, return that orbiter to Earth, release the sample container to re-enter Earth's atmosphere, recover the samples and quarantine them for analysis. Every step is technically challenging. Every step has never been done before, at least not for Mars samples. We've returned samples from the Moon and from asteroids, but Mars is harder. The samples Perseverance is collecting include rocks from the ancient delta, which might contain organic molecules or even biosignatures, sedimentary rocks that formed in water, volcanic rocks that record Mars' geological history, even an atmospheric sample, a tube sealed with Martian air inside. These samples could answer fundamental questions. Did life ever exist on Mars? What was Mars' climate like billions of years ago? What resources are available for future missions? How similar or different is Martian geology from Earth's? But they're also insurance. Even with all of Perseverance's sophisticated instruments, there are analyses that can only be done in Earth laboratories. Isotope ratios that require mass spectrometers too large to fly to Mars. Microscopy at resolutions too fine for rover cameras. Chemical analyses that need extensive sample preparation. If we can return these samples, we can apply the full power of terrestrial science to them. Hundreds of laboratories, thousands of scientists, techniques that won't be invented for years yet, but will be available when the samples finally arrive. The samples are sealed, labeled, stored safely in Perseverance's belly. And in a few locations, Perseverance has also deposited backup samples on the Martian surface, a safety net in case something happens to the rover. They're waiting. Pieces of Mars, carefully selected and preserved, ready for the journey home. If the sample return mission succeeds, these rocks will be the most studied geological samples in history. Every atom analyzed, every mineral grain examined, and maybe, just maybe, they'll contain answers to questions we've been asking since we first looked up at that red dot in the sky and wondered, are we alone? Mars has been observed since ancient times. Babylonian astronomers tracked its movement across the sky over 4,000 years ago, recording its positions in clay tablets that survive today. They noticed something strange. Mars moves differently than the stars. The stars are fixed, rotating predictably with the seasons. But Mars wanders. The word planet comes from the Greek word for wanderer. Even stranger, Mars sometimes appears to move backwards. It travels eastward across the sky for months, then stops, moves westward for a few weeks, stops again, and resumes its eastward motion. This retrograde motion puzzled ancient astronomers for centuries. We now understand why this happens. Both Earth and Mars orbit the Sun, but at different speeds and distances. When Earth, which moves faster, overtakes Mars in its orbit, Mars appears to move backwards relative to the background stars, the same way a car you're passing appears to move backwards relative to distant trees. But ancient astronomers didn't have that framework. They struggled to explain retrograde motion using Earth-centered models, creating elaborate systems of epicycles, circles within circles, to account for Mars' wandering path. The ancient Egyptians associated Mars with war and destruction, calling it Hardacher, the Red One. The Babylonians called it Nergal. The Greeks called it Ares. The Romans, Mars. All warrior gods, all associated with conflict and bloodshed because of that distinctive red color. In 1610, Galileo turned his telescope toward Mars and became the first person to observe it as more than a point of light. He couldn't make out surface features. His telescope wasn't powerful enough, but he could see that Mars was a disk, a world, not just a star. Centuries of progressively better observations followed. Astronomers mapped dark and light features, thinking they were seeing continents and seas. They tracked the polar ice caps growing and shrinking with seasons. They measured Mars's rotation period. They documented dust storms. And through all of this, Mars remained mysterious, close enough to see, far enough to hide its secrets, red enough to capture imagination, strange enough to inspire speculation. For thousands of years, humans have watched Mars, wondered about it, made up stories about it, and now finally we're there, walking its surface through rovers, flying through its air with helicopters, preparing to send humans, from clay tablets to spacecraft, from mythology to geology, from wondering what Mars is to knowing with increasing precision what it was and might become. The same red dot ancient Babylonians tracked is the world where our robots now explore, connected across millennia by curiosity. When Galileo first pointed his telescope at Mars in 1610, he saw something that shocked him. Mars wasn't a point of light like the stars. It was a disk. Small, blurry, but definitely a disk with measurable size. This was profound. It meant Mars was a world, a physical place with dimensions and possibly features, not just a wandering light in the heavens. But Galileo's telescope, with only about 30x magnification, couldn't resolve any surface details. Mars appeared as a fuzzy red-orange circle. No markings, no polar caps, nothing to suggest what kind of world it might be. Still, the observations supported the Copernican model, the heretical idea that Earth wasn't the center of the universe. If Mars was a world, perhaps similar to Earth, then maybe Earth was just another planet. Maybe the Sun, not Earth, was the center of the solar system. It would take another 250 years before telescopes improved enough to see actual surface features on Mars. In the mid-1800s, astronomers began mapping dark and light regions, which they thought were continents and seas. They tracked the polar ice caps. They measured the length of Mars' day. And in 1877, Italian astronomer Giovanni Schiaparelli created detailed maps of Mars showing what he called canali, channels. The word was mistranslated into English as canals, implying artificial construction rather than natural formations. This mistranslation sparked decades of speculation. If there were canals on Mars, that meant intelligent life, a civilization, engineers capable of massive construction projects, perhaps a dying civilization on a drying planet, desperately building irrigation systems to transport water from the polar ice caps to equatorial cities. Percival Lowell, a wealthy American astronomer, became obsessed with this idea. He built an entire observatory in Flagstaff, Arizona, dedicated to studying Mars. He drew elaborate maps showing geometric patterns of intersecting canals. He wrote books arguing that Mars was inhabited by an advanced but struggling civilization. The canals, of course, didn't exist. They were optical illusions, the human brain's tendency to connect random dark patches into linear patterns. When telescopes improved further, the canals disappeared, replaced by the actual features of Martian terrain. But the episode shows how eager we were to find life on Mars, how willing to interpret ambiguous observations as evidence of intelligence, how much we wanted Mars to be inhabited, not just by microbes, but by beings we could understand, relate to, maybe even communicate with. From Galileo's blurry disk to Schiaparelli's canals to today's high-resolution orbital imagery, our view of Mars has sharpened dramatically. But the desire remains the same, to know what's there, to find out if we're alone, to discover whether Mars is, has been, or could be home to life. In 1877, during a particularly close approach of Mars to Earth, Italian astronomer Giovanni Schiaparelli observed the planet with his 8-inch telescope and reported seeing canali, an Italian word meaning channels or grooves. When his observations were published, The word was translated into English as canals, which has very different implications. Channels can be natural, carved by water or lava. Canals are artificial, built by intelligent beings. This single mistranslation changed how people thought about Mars for decades. Schiaparelli himself was cautious about the interpretation. He never claimed the features were artificial. He just recorded what he saw, or thought he saw, through his telescope. A network of straight, dark lines crisscrossing the Martian surface. But others weren't so cautious. Percival Lowell, in particular, became convinced that the canals were real and artificial. He argued that Mars was an ancient, dying world, its water disappearing, its civilization desperately engineering massive irrigation systems to survive. Lowell drew incredibly detailed maps of Mars showing hundreds of canals arranged in geometric patterns, networks of lines connecting circular regions he called oases. He wrote passionately about the Martians' engineering prowess, their struggle against a hostile environment, their inevitable decline. The canals captured public imagination. Science fiction writers seized on the idea. H.G. Wells wrote The War of the Worlds, imagining desperate Martians invading Earth to escape their dying planet. Edgar Rice Burroughs wrote his Barsoom series about adventures on a Mars filled with canals and ancient cities. But as telescopes improved, the canals became harder to see. Some astronomers reported them, others didn't. Photographs taken with the best equipment showed no canals at all, just random dark patches. By the early 20th century, most scientists had concluded that the canals were optical illusions. The human eye and brain, when staring at the limits of visibility, tend to connect disconnected features into patterns. Lowell was essentially seeing what he expected to see, connecting random, dark regions into the linear patterns he believed should be there. The canals were never real, but they felt real to those who observed them, and they shaped popular perceptions of Mars for generations. Even today, canals on Mars is cultural shorthand for mistaken but appealing beliefs, for seeing what we want to see, for letting expectation shape observation. But here's what's interesting. Schiaparelli and Lowell weren't wrong about everything. Mars did have water. Ancient riverbeds do exist. We just call them channels or valleys. And they were carved by water billions of years ago, not by Martian engineers thousands of years ago. The canals were an illusion, but the desire to find evidence of life, of intelligence, of beings we could relate to, that was real. And that desire still drives Mars exploration today, even though we're searching for microbes now, not canal builders. Percival Lowell was so obsessed with Mars that he built an entire observatory dedicated to studying it. He chose Flagstaff, Arizona, for its high altitude and clear, steady air, some of the best astronomical seeing conditions in the United States. He installed a 24-inch refracting telescope, one of the finest instruments of its era, and he dedicated years of his life to observing Mars, mapping its features, and arguing for the existence of Martian civilization. Lowell Observatory, founded in 1894, still exists today. It's become a respected research institution, famous for more than just Lowell's Martian obsession. In 1930, astronomer Clyde Tombaugh discovered Pluto from Lowell Observatory, the first new planet found in nearly a century, though Pluto was later reclassified as a dwarf planet. But in Lowell's time, the observatory was primarily a platform for studying Mars. Lowell wrote 3 books about the planet: Mars, 1895, Mars and Its Canals, 1906, and Mars as the Abode of Life, 1908. He argued passionately. The canals were too straight to be natural. They were too organized. They showed evidence of intelligent design. The seasonal darkening of certain regions suggested vegetation growing when water arrived through the canals. The whole system was an enormous engineering project by a civilization trying to survive on a drying world. Most scientists disagreed with him, but Lowell was wealthy, articulate, and persistent. He gave lectures, published popular articles, made Mars relevant to public discourse in ways that academic astronomy rarely achieved. And in a strange way, he was right about the important part. Mars was worth studying intensively. It did have a fascinating history. It was relevant to understanding Earth and life and planetary evolution. He was just wrong about the specifics. The canals didn't exist. The Martians weren't there. But his enthusiasm, his willingness to build an entire observatory and dedicate his life to Mars, helped keep Mars at the forefront of astronomical research. Today, Lowell Observatory continues operating. The telescope Lowell used is still there, preserved. You can look through it and see Mars the way he saw it, blurry, red, mysterious. And you can understand how someone staring at those fuzzy images night after night might start to see patterns, might start to believe. Lowell died in 1916, still convinced the canals were real. He never knew that Mars exploration would eventually prove him wrong about the canals, but vindicate his belief that Mars had once been wetter, more hospitable, perhaps even habitable. The observatory stands as a monument to obsession. Sometimes obsession is misguided, but sometimes it builds telescopes and advances science, even when the specific theories turn out to be wrong. In July 1965, NASA's Mariner 4 spacecraft flew past Mars and transmitted the first close-up images of another planet. The images were disappointing in a way. People had hoped for, if not canals and cities, at least interesting terrain, maybe lakes, signs of weathering, something exciting. Instead, Mariner 4 showed a moon-like landscape, heavily cratered, dead, lifeless, no canals, no vegetation, no obvious signs that Mars was anything more than a cold, dead rock. The spacecraft took 22 images total, very low resolution by today's standards, about 200 meters per pixel, but they were clear enough to show crater after crater, suggesting Mars had been geologically dead for billions of years. It was a profound disappointment. The romantic vision of Mars, the dying civilization, the ancient canals, even the possibility of simple vegetation, died with those images. Mars, it seemed, was as dead as the moon. Science fiction had to adjust. Stories about Martian civilizations suddenly felt dated. Mars became a place for human colonization in fiction, not a place to meet native inhabitants. But as more spacecraft visited Mars, more mariners than Vikings, a more complex picture emerged. Yes, Mars is heavily cratered in some regions, but other regions show signs of water erosion, evidence of ancient rivers, possible ocean shorelines. Mars wasn't as dead as Mariner 4's limited sample suggested. Still, Mariner 4 was a watershed moment. The first time humans saw another planet up close. The first time romantic speculation collided with hard data. The first time we had to reckon with Mars as it actually is, not as we imagined it. The spacecraft is still out there somewhere, in solar orbit, its mission long complete, its cameras silent, its transmitter cold. But those 22 grainy images changed everything. They closed one chapter of Mars exploration, the era of speculation, and opened another, the era of direct observation. No more canals, no more Martians, just a planet waiting to reveal its real secrets. When the Viking landers touched down on Mars in 1976, they carried something unprecedented. Experiments specifically designed to detect life. Not fossils, not traces of ancient biology, but living organisms actively metabolizing right there in the Martian soil. There were 3 main life detection experiments. The labeled release experiment added radioactive nutrients to soil samples and watched for gases that would indicate biological metabolism. The pyrolytic release experiment tested whether Martian organisms could incorporate carbon dioxide into organic molecules, mimicking photosynthesis. The gas exchange experiment monitored changes in atmospheric composition when soil was exposed to nutrients and water. The results were complicated. The labeled release experiment showed positive results. When nutrients were added to Martian soil, the sample released radioactive carbon dioxide, exactly what you'd expect if microbes were consuming the nutrients and exhaling CO2. But the control tests produced confusing data. When the soil was sterilized by heating, the reaction stopped, which seemed to support a biological interpretation. But when the experiment was repeated with variations, the results didn't match what biology would predict. The reaction happened too quickly. It was too vigorous. And it happened even in samples that seemed too harsh to support life. The gas exchange experiment also showed unusual results. When Martian soil was exposed to water vapor, it released oxygen, lots of oxygen, more than could be easily explained by known chemistry. The scientific consensus eventually settled on a non-biological explanation. Mars's soil contains highly reactive chemicals, probably perchlorates and superoxides created by ultraviolet radiation, that mimic biological activity when exposed to water and nutrients. The Viking experiments detected chemistry, not life. But here's the thing, not everyone agrees. The principal investigator of the labeled release experiment, Gilbert Levin, remained convinced until his death in 2021 that Viking had detected life. He argued that the results matched biological predictions, that alternative explanations were contrived, that we were dismissing positive results because they seemed impossible. Most scientists disagree with him. The consensus is that Viking's experiments were ingeniously designed, but ultimately ambiguous, capable of detecting chemistry that looks like biology, but unable to definitively distinguish between the two. Still, the ambiguity remains. We've never sent another life detection experiment to Mars. We've sent mineralogy experiments, organic molecule detectors, cameras and spectrometers, but nothing specifically designed to catch microbes in the act of living. Maybe Viking detected weird Martian chemistry, or maybe, just maybe, it detected life, and we talked ourselves out of believing it because the implications were too enormous. The truth is, we don't know, and that uncertainty, decades later, still haunts Mars exploration. Did we find life on Mars in 1976 and dismiss it? Or did we learn an important lesson about how alien chemistry can fool biology detecting instruments? The Viking landers are still there, silent monuments on Chryse Planitia and Utopia Planitia. Their experiments are over, their batteries dead. But the questions they raised remain very much alive. Over 350 meteorites found on Earth originated from Mars. We hold pieces of Mars in our hands. We can study them in laboratories. We can analyze them with instruments too large and sophisticated to send to Mars. These are rocks that were blasted off Mars by asteroid impacts. Violent collisions that excavated craters and flung debris into space at speeds exceeding Mars' escape velocity. They wandered through the solar system, some for just a few million years, others for hundreds of millions, until their orbits intersected Earth's. How do we know they're from Mars? Several ways. The gases trapped in tiny pockets within these meteorites match the atmospheric composition of Mars as measured by the Viking landers. The ratio of different isotopes of noble gases, argon, xenon, krypton, is distinctive enough to serve as a fingerprint. The crystallization ages of minerals in these meteorites match the ages of Martian volcanic rocks, not Earth rocks or moon rocks or asteroid material. The meteorites contain minerals and textures consistent with formation in a low-gravity environment with a thin atmosphere, consistent with Mars, not Earth. These Martian meteorites are extraordinarily valuable scientifically. They're free sample return missions. Nature did the hard work of launching rocks from Mars and delivering them to Earth. All we had to do was find them. Most Martian meteorites are igneous rocks, basalts, and other volcanic materials. They tell us about Mars' interior composition, the chemistry of its mantle, the processes that drove volcanism billions of years ago. But they're also intensely studied for signs of biology. Every grain is scrutinized under microscopes. Every organic molecule is analyzed. Every crystal structure is examined for anomalies that might suggest biological influence. Some of these meteorites are quite beautiful. Polished sections reveal colorful minerals, green olivine, black pyroxene, reddish iron oxides. They look alien, which in a sense they are. Rocks that formed on another planet, carrying stories written in their atomic structure. You can actually buy small pieces of Martian meteorites from mineral dealers. They're expensive, thousands of dollars per gram, but they're available. You can hold a piece of Mars, feel its weight, look at it under magnification, connect physically to another world. There are Martian meteorites sitting in museum collections, in university laboratories, in private collections around the world, each one a messenger, each one carrying information about Mars' past that we're still learning to decode. And somewhere on Mars, there are impact craters where these rocks came from. We'll probably never find them. They could be anywhere, and billions of years of erosion have obscured their features. But they exist. Connection points between worlds, written in violence and preserved in stone. One Martian meteorite became famous, or infamous, depending on your perspective. Its designation is ALH 84001, found in Antarctica in 1984. It's ancient, about 4 billion years old, from Mars's early history when the planet was warmer and wetter. It's also unusual. While most Martian meteorites are volcanic basalts, ALH 84001 is an orthopyroxenite, a rock type that forms deep in planetary crusts. In 1996, a team of scientists published a paper in the journal Science Making an Extraordinary Claim. ALH 84001 might contain evidence of ancient Martian life. Their evidence was circumstantial but intriguing. The meteorite contains carbonate minerals that appear to have formed in liquid water at relatively low temperatures, conditions potentially suitable for life. It contains polycyclic aromatic hydrocarbons, PAHs, organic molecules that on Earth are often associated with biological decay. Under extremely high-resolution electron microscopy, the carbonates show tiny structures, less than 100 nanometers long, that vaguely resemble bacteria. The meteorite contains tiny crystals of magnetite and iron sulfide, arranged in ways that on Earth are produced by certain bacteria. The announcement was huge. President Clinton gave a speech about it. NASA held press conferences. The possibility that we'd found evidence of Martian life, actual fossils preserved in a rock and delivered to Earth by cosmic accident, captured global attention. But skepticism followed quickly. Other scientists examined the meteorite and offered alternative explanations for each piece of evidence. The PAHs might be terrestrial contamination from Antarctic ice, not Martian organics. The tiny structures might not be fossils, but rather mineral formations that happen to look biological. The same pareidolia that makes us see faces in random patterns. The magnetite crystals could form through non-biological high-temperature processes. The carbonates might have formed at temperatures too high for life, not the low temperatures initially claimed. Over the following years, the biological interpretation became increasingly untenable. Most scientists now think ALH 84001's features are probably non-biological, formed by geological and chemical processes that don't require life. But the debate isn't completely settled. A few researchers still argue that the biological hypothesis deserves consideration, and even those who think the features are non-biological admit that we don't fully understand all the formation mechanisms. ALH 84001 taught us important lessons. It showed us how difficult it is to prove past life from ambiguous evidence, how easily we can see what we want to see, how important it is to rule out non-biological explanations before claiming biology. It also showed us how desperately we want to find life on Mars. The announcement captured attention in ways that purely geological discoveries rarely do. We care about whether we're alone. We care deeply. The meteorite still exists, carefully preserved, still studied, still yielding insights about early Mars, even if those insights don't include life. And the question it raised remains. If we find similar features in samples returned directly from Mars, carbonates, organic molecules, tiny structures that might be fossils, will we be able to tell the difference between biology and geology? Or will we face the same ambiguity, the same uncertainty, the same difficulty distinguishing life from chemistry? Mars releases mysterious plumes of methane that appear seasonally, peak in certain regions, and then dissipate quickly. And we don't know why. Methane is interesting because it's unstable in Mars' atmosphere. Ultraviolet light from the sun breaks it down relatively quickly, within a few hundred years, which is geologically instantaneous. So if there's methane in the atmosphere, something must be producing it right now. It can't be ancient methane lingering from billions of years ago. On Earth, most methane comes from biological sources: bacteria in wetlands, digestive processes in animals, decay of organic matter. Some comes from geological sources: volcanic activity, serpentinization reactions where water interacts with certain minerals. Mars has no cows, no wetlands, no obvious sources of biological methane production, but the Curiosity rover has detected methane spikes, periods where atmospheric methane concentrations rise significantly above background levels, then drop back down. The detections are real. Multiple instruments have confirmed them. Curiosity's tunable laser spectrometer detected seasonal variations with methane levels spiking in late summer. The European Space Agency's Mars Express orbiter detected regional plumes from space. But here's what's puzzling. the methane appears and disappears too quickly. If it's being released from underground, atmospheric circulation should distribute it more evenly. Instead, it forms localized plumes that dissipate rapidly. Several explanations have been proposed. Biological, methane-producing microbes living in underground refuges, releasing gas that seeps to the surface. This is the exciting explanation, but requires Mars to have active microbial ecosystems right now. Geological, serpentinization reactions occurring in subsurface water, producing methane through chemistry alone. This requires liquid water underground, which is possible but unproven. Clathrates. Methane trapped in ice structures, occasionally released when those structures destabilize. This could explain seasonal variations if temperature changes trigger release. Impact-related. Organic molecules delivered by micrometeorites, breaking down to produce methane. This seems unlikely to produce the observed concentrations and patterns. The mystery deepens because we can't seem to catch the methane in the act. Curiosity detects it at ground level. Orbiting spacecraft sometimes detect plumes from above, but pinpointing sources has proven elusive. If the methane is biological, it would be one of the most important discoveries in history. If it's geological, it's still fascinating. Evidence of active chemistry, possibly involving liquid water, happening on Mars today. But we don't know. The methane appears, disappears, teases us with possibilities, and Mars keeps its secrets. Future missions might carry more sophisticated instruments capable of isotopically analyzing the methane, determining whether it's biological or geological based on the ratio of carbon-12 to carbon-13. Biological methane tends to be enriched in the lighter isotope. Geological methane has different isotopic signatures. Until then, the methane remains a mystery, a tantalizing hint that Mars might not be as geologically or biologically dead as it appears, a reminder that the planet still has surprises to reveal. In 2018, scientists using ground-penetrating radar detected what might be liquid water beneath Mars' south polar ice cap. The signal came from a region about 12 miles across, sitting beneath more than a mile of ice. The radar reflection looked exactly like what you'd expect from liquid water. A bright, smooth interface indicating a substance with very different electrical properties than ice. If confirmed, this would be a subglacial lake, similar to Lake Vostok and other lakes beneath Antarctica's ice sheet. A body of liquid water trapped beneath ice, isolated from the surface, possibly existing for millions of years. How can water be liquid under those conditions? Mars's south polar region is incredibly cold. Temperatures at the surface drop below 200 degrees RT in winter. Ice that deep would be under enormous pressure, but not enough by itself to keep water liquid. The answer probably involves salts. Perchlorates or other salts dissolved in the water would dramatically lower its freezing point. A concentrated brine might remain liquid at temperatures well below 0 degrees, even under Martian conditions. But the discovery is controversial. Some scientists question whether the radar data really indicates liquid water. Alternative explanations include clay layers, volcanic materials, or other substances that might produce similar radar signatures. Follow-up observations have both supported and complicated the initial finding. Some studies detected additional potential subglacial lakes nearby. Others suggested the radar signals might be explained by other materials. The debate continues, but if the subglacial lake is real, The implications are profound. First, it would be one of the only places on modern Mars where substantial liquid water exists. Not temporary brines seeping down slopes, but an actual lake with volume and persistence. Second, it would be a potential habitat. On Earth, subglacial lakes beneath Antarctica host microbial life. Extremophiles adapted to cold, darkness, and isolation. If life exists on Mars today, a subglacial lake would be a logical place to look. Third, it would raise questions about how to explore such environments without contaminating them. Drilling through miles of ice on Mars would be technologically challenging. Doing so without introducing Earth microbes would be even harder. The lake, if it exists, has been isolated for potentially millions of years. Its chemistry might be unique. Its microbiology, if any exists, could be fundamentally different from Earth life, having evolved independently in isolation. Or it might be sterile, cold, dark, salty, chemically active but biologically dead. A fascinating environment, but not a living one. We don't know. The radar keeps pinging. The data keeps accumulating. Scientists keep debating interpretations. And beneath miles of ice at Mars's south pole, something, water or mineral deposits or something else, sits in the darkness, waiting. The Mars Reconnaissance Orbiter's spectrometers have detected clay minerals across ancient Martian terrain. Minerals that only form when volcanic rock interacts with liquid water over extended periods. Not just any water. Neutral pH water. Not too acidic, not too basic. The kind of water that's habitable by Earth standards. Clays form through weathering, a slow process where water chemically alters rock. On Earth, this happens everywhere. Water and rock meet over time. Rain falls. Water seeps through soil. Chemical reactions occur. Minerals transform. Clays accumulate. On Mars, the widespread presence of clays tells us that ancient Mars wasn't just occasionally wet. It had persistent water, groundwater or surface water that interacted with rocks for thousands or millions of years. The Curiosity rover has found clay minerals in Gale Crater's lakebed deposits. Orbital observations show clays in crater walls, valley networks, and ancient highlands. They're particularly common in terrain dating to Mars's early history, 3.5 to 4 billion years ago. This is evidence for the warm and wet early Mars hypothesis. The planet wasn't just occasionally drizzled with water. It had a climate that supported long-term aqueous chemistry, possibly rainfall, definitely persistent groundwater, maybe lakes or seas, and the chemistry was benign. Some Martian minerals formed in acidic conditions, sulfates that suggest evaporating acidic brines. But clays indicate neutral pH, water chemistry that wouldn't immediately destroy organic molecules or cell membranes. From a habitability perspective, this is crucial. Life requires liquid water, but not just any water. Extremely acidic or basic water damages biological molecules. Salty water creates osmotic stress. But neutral pH water with moderate salinity, the conditions that formed these clays, is the kind of water where life thrives on Earth. The clays are ancient. They formed billions of years ago and have been preserved, buried under younger rocks or protected in crater walls. But they're still there, still chemically intact, still carrying information about the water that created them. Future missions might target clay-rich regions specifically. If we're searching for biosignatures, chemical or physical evidence of past life, clay minerals are good places to look. on Earth, clays preserve organic molecules, sometimes for millions of years. If Mars had life during the clay-forming era, those clays might have trapped and preserved biological material. The presence of clays also matters for future colonization. Clays contain water bound in their crystal structure, not free liquid water, but hydrogen and oxygen chemically incorporated into minerals. That water can be extracted by heating, a resource for future astronauts, locked in ancient rocks, waiting to be liberated. Mars's clays remember a wetter time. They're fossils, not of life, but of water. Evidence written in altered minerals, testifying to a world that once had the chemistry needed for biology. Even if biology never arose to take advantage of it, some scientists propose that Mars once had plate tectonics, Earth-style movement of crustal plates, with subduction zones, spreading centers, and continental drift. The evidence is ambiguous. Unlike Earth, Mars doesn't have obvious mid-ocean ridges or deep trenches. Its surface is ancient and heavily cratered, without the continuous recycling that plate tectonics provides. But there are hints. Some regions show linear features that might be ancient plate boundaries. Magnetic anomalies form stripes in certain areas, similar to Earth's seafloor spreading patterns. Some of Mars's early crust might have been mobile before freezing into place. If Mars had plate tectonics, it would have been early in its history, perhaps only the first few 100 million years after formation. Then, as the planet's interior cooled, convection in the mantle weakened, and the system shut down. The crust froze. Plates stopped moving. Mars became a single-plate planet, geologically stagnant. This would explain several puzzles. Why Mars has such diverse terrain, some regions heavily cratered and ancient, others smooth and younger. Why volcanism continued in certain regions, while others remained dormant. Why the magnetic field shut down. Plate tectonics helps drive core convection, and losing it might have caused the dynamo to fail. On Earth, plate tectonics is crucial for long-term habitability. It recycles carbon dioxide, regulating atmospheric composition. It creates diverse environments, mountains, valleys, coastlines. It drives volcanism, which releases gases that replenish atmosphere. It generates heat and chemical energy that life can exploit. If Mars had plate tectonics and then lost it, that might explain the planet's climate transition. Early Mars with active tectonics could have maintained a thick atmosphere and warm climate. When tectonics stopped, atmospheric recycling ended, volcanism declined, and Mars gradually froze. But this is speculative. We don't have definitive proof that Mars ever had plate tectonics. The features that suggest it could have other explanations. Mars might have always been a stagnant lid planet, like Venus or Mercury, where the crust never broke into moving plates. Still, the hypothesis is worth considering. Because if Mars had plate tectonics and lost them, it might tell us something important about Earth. Our planet has had active plate tectonics for billions of years. But is it permanent? Could Earth's tectonics eventually shut down as the interior cools? And if so, what would happen to our climate, our biosphere, our habitability? Mars might be a cautionary tale, a world that once had the dynamic geology needed for long-term habitability, then lost it. A reminder that planets aren't static. They evolve, and sometimes that evolution leads away from conditions favorable to life. Phobos and Deimos are strange moons, and scientists aren't certain where they came from. One hypothesis: they're captured asteroids. wanderers from the asteroid belt that passed too close to Mars and were gravitationally captured into orbit. They look like asteroids, small, potato-shaped, heavily cratered. Their composition seems similar to carbonaceous asteroids. Capture makes sense, except capture is hard. For Mars to capture passing asteroids and place them into the nearly circular, nearly equatorial orbits we observe, conditions would need to be just right. Most capture scenarios result in highly elliptical orbits, or orbits at steep angles to the equator. Phobos and Deimos orbit almost in Mars' equatorial plane, almost circularly, improbable for captured objects. Alternative hypothesis: they formed along with Mars from the same disk of material that created the planet. But their composition doesn't quite match Mars. And why would Mars only form 2 tiny moons, while Earth formed 1 large moon? Another hypothesis gaining favor: they're remnants of a larger moon that was destroyed. Early in Mars's history, a massive impact might have created a debris disk around the planet, similar to how Earth's moon formed. That debris coalesced into a large moon, which then spiraled inward due to tidal forces and was torn apart when it crossed Mars-Roche limit. Phobos and Deimos are the scattered remnants, the only pieces that ended up in stable orbits. This would explain their orbits. They're in Mars' equatorial plane because they formed from debris that was already in that plane. It might explain their composition, which is somewhat similar to Martian crust material mixed with impactor material. The truth is, we're not sure. We've never returned samples from Phobos or Deimos. We've only photographed them from orbit and from passing spacecraft. They remain mysterious. 2 small, dark rocks circling Mars, their origin unknown. Future missions might visit them directly. Russia has proposed a Phobos sample return mission. Japan's space agency has considered a Martian moon's exploration mission. If we could bring back pieces of Phobos or Deimos, analyze them in terrestrial laboratories, we might finally answer the question: where did Mars moons come from? Until then, they remain orphans of uncertain parentage, born from the asteroid belt or from Mars or from a destroyed moon, children of capture, accretion, or catastrophe, fear and panic forever circling Mars, keeping their origins secret. Curiosity rover has detected organic molecules in Martian rocks, carbon-based compounds that are the building blocks of life as we know it. Not life, not fossils, just organic molecules. But their presence is significant. Organic molecules are simply compounds containing carbon bonded to hydrogen, often with other elements like oxygen, nitrogen, sulfur. On Earth, they're primarily produced by life: proteins, lipids, DNA, all the molecular machinery of biology. But they can also form through non-biological processes, in space, in comets, through chemical reactions in rocks. The molecules Curiosity detected include thiophanes, benzene, toluene, and small carbon chains. They were found in ancient lakebed rocks in Gale Crater, rocks that formed 3.5 billion years ago when water filled the crater. Where did they come from? 3 possibilities: biological, produced by ancient Martian microbes, then preserved in the rocks for billions of years. This is the exciting interpretation, but requires life to have existed. Meteoritic, delivered by carbonaceous meteorites that constantly bombard Mars. Organic molecules from space incorporated into rocks. Non-biological but extraterrestrial. Geological, formed through chemical reactions between water, minerals, and gases in Martian rocks. Non-biological and indigenous to Mars. We can't yet distinguish between these possibilities. Curiosity's instruments can detect organic molecules, but can't determine their origin definitively. That would require more sophisticated analysis. Isotopic ratios, molecular structures, contextual evidence that might only be possible with samples returned to Earth. But the presence of organics is encouraging. It means Mars had, and perhaps still has, active carbon chemistry. That complex organic molecules can form and persist on Mars. That the building blocks for life were available, if life ever took advantage of them. One concern was that Mars's surface is bombarded by ultraviolet radiation and oxidizing chemicals that should destroy organic molecules. The fact that Curiosity found them, especially in ancient rocks, suggests either they're being protected, buried quickly, shielded from radiation, or they're being continuously produced by some active process. The molecules are simple by biological standards, nothing as complex as proteins or nucleic acids, but they're a start. Evidence that Mars isn't chemically sterile, that carbon chemistry happens there, has happened there, might still be happening there. And if we find more complex organics, especially in patterns that suggest biological assembly, that would strengthen the case for past life. Biology creates specific patterns of molecules, specific chirality, handedness, specific complexity. Chemistry alone rarely creates those patterns. Curiosity keeps drilling, keeps analyzing, keeps finding organic molecules in rock after rock. Each discovery adds to the chemical inventory of Mars. Each one raises the question, are we seeing the chemistry of a sterile world, or the fossil chemistry of a world that once lived? Ancient Mars had a much stronger greenhouse effect from carbon dioxide, which allowed liquid water to exist despite Mars receiving less sunlight than Earth. Mars is about 50% farther from the Sun than Earth is. That means it receives only about 43% as much solar energy per unit area. Today, that insufficient sunlight, combined with thin atmosphere, makes Mars frozen. But 3.5 to 4 billion years ago, Mars apparently had liquid water on its surface. Rivers flowed, lakes persisted, an ocean might have covered the northern lowlands. How? The most likely answer, a thicker atmosphere with much more carbon dioxide. CO2 is a greenhouse gas. It allows visible light from the sun to reach the surface, but traps infrared radiation, heat, trying to escape back into space. With enough CO2, estimates range from tens to hundreds of times more than Mars' current atmospheric pressure. The greenhouse effect could have warmed Mars sufficiently for liquid water, even at its greater distance from the sun. But this creates a puzzle. Where did all that CO2 go? Mars's current atmosphere is 95% CO2, but the total atmospheric pressure is only about 1% of Earth's. If Mars once had much more CO2, it was either lost to space or locked away in rocks. Some was definitely lost to space. Without a magnetic field to protect it, solar winds stripped away significant amounts of atmosphere over billions of years. NASA's MAVEN spacecraft has measured this ongoing loss, about 100 grams of atmosphere escaping per second even today. But some CO2 likely got incorporated into rocks. Carbonate minerals form when CO2 dissolves in water and reacts with calcium and other elements. On Earth, this process continuously removes CO2 from the atmosphere and locks it in limestone and other rocks. Mars should have abundant carbonates if it once had a thick CO2 atmosphere and liquid water. But we don't see extensive carbonate deposits. They exist, we've detected them, but not in the quantities expected. This is one of the mysteries of early Mars. The planet apparently had enough atmospheric CO2 to create greenhouse warming, but we can't fully account for where that CO2 went. Maybe it's buried, mixed into polar ice, trapped in subsurface minerals, hidden in regions we haven't fully explored. Maybe more was lost to space than models predict. Maybe additional greenhouse gases, methane, hydrogen, supplemented CO2's warming effect. Whatever the mechanism, early Mars was warm enough for liquid water. Not tropical, probably still cold by Earth standards, perhaps like Earth's Arctic or Antarctic, but warm enough, wet enough, habitable enough. Then that thick atmosphere thinned, the greenhouse effect weakened, temperatures dropped, water froze or evaporated, and Mars transformed into the frozen desert we see today. The planet once had a blanket, a thick atmosphere that held in warmth. Then that blanket gradually thinned and disappeared, and Mars, exposed to the cold of space, began its long freeze. Some models suggest early Mars had rainfall, actual precipitation cycles, with water evaporating from surfaces, forming clouds, and falling back down as rain. This isn't science fiction. It's hydrology, extrapolated from evidence. The valley networks on Mars, those branching dendritic patterns that look like river systems, match patterns created by rainfall erosion, not just by groundwater seepage or catastrophic floods. On Earth, when rain falls on landscapes, it creates specific erosion patterns. Water collects in small channels that merge into larger channels, forming tree-like drainage networks. The spacing between tributaries, the angles at which they merge, the density of the network, all follow predictable patterns determined by rainfall intensity, soil properties, and topography. Some Martian valleys match these patterns almost perfectly. The implication is that rain fell on Mars, collected in channels, carved valleys, and flowed toward lowlands, just like on Earth. Imagine it, gray clouds forming over ancient Martian highlands, condensation, precipitation, drops of water falling through thin but adequate atmosphere, hitting the ground, pooling, flowing downhill. The sound of rainfall, which would have been quieter than on Earth due to thinner air, but still present. The rain wouldn't have been gentle. Models suggest that in Mars's lower gravity and thinner atmosphere, raindrops would have grown larger before falling, possibly several millimeters in diameter. They would have fallen slower than Earth raindrops, but hit with significant impact, eroding soil and rock. And this wasn't a brief period. The valley networks are extensive, deeply carved. To create such features requires sustained rainfall over thousands or millions of years, long enough for climate patterns to establish, long enough for complete hydrological cycles, evaporation, condensation, precipitation, runoff, to operate. Early Mars might have had seasons with more rain and seasons with less. Rainy periods when valleys filled and flowed, dry periods when water levels dropped and flows diminished. A climate with patterns, rhythms, predictability. Then, as the atmosphere thinned and temperatures dropped, the rainfall became less frequent, more sporadic, eventually rare enough that it couldn't maintain the river networks. The valleys stopped flowing, lakes evaporated or froze, the landscape dried out. The last rain on Mars probably fell billions of years ago, a final shower, soaking into dust, evaporating quickly, never repeated. After that, only ice and occasionally liquid water from melting, but no more rain from clouds. those ancient valleys remain, dry and windswept, recording a time when water fell from Martian skies. When the planet had weather that resembled Earth's, at least superficially. When you could have stood on Mars and felt rain on your spacesuit, watched puddles form, listened to the trickle of flowing water. A Mars we never saw, a Mars that ended long, before humans evolved to wonder about it. The lack of plate tectonics on Mars means its volcanoes grew to enormous sizes, building up over millions of years as lava repeatedly flowed from the same locations. On Earth, volcanic hotspots are relatively stationary in the mantle, but the crust moves over them due to plate tectonics. This creates chains of volcanoes, like the Hawaiian Islands. Each island is a volcano that formed over the hotspot, then got carried away by the moving Pacific plate. The hotspot stays put, creating a new volcano, which in turn gets carried away. This limits how large any individual volcano can grow. It might be active for a few million years before plate motion carries it away from its magma source. But Mars has no plate tectonics. Its crust is stationary. So when a volcanic hotspot starts erupting, it keeps erupting in the same location for hundreds of millions of years. Lava piles up, layer after layer, flow after flow. The volcano grows vertically, building height rather than spreading horizontally. This is why Olympus Mons is so enormous. It's been building for perhaps 200 million years or more, possibly with intermittent activity continuing until relatively recently, maybe as recently as 20 million years ago, which is geologically very recent. The same is true for the Tharsis volcanic region, which contains multiple enormous volcanoes. Arsya Mons, Pavonis Mons, Askreus Mons. They're all shield volcanoes, similar to Hawaii's volcanoes but vastly larger, built over millions of years from the same magma sources. These volcanoes might not be extinct. We haven't detected active eruptions, but that doesn't mean they couldn't erupt again. The magma chambers beneath might still be hot. The next eruption might be thousands or millions of years away. Or it might happen tomorrow. We don't know. If Mars volcanoes are still active, even sporadically, that would have implications for habitability. Volcanic eruptions release heat, gases, and minerals. They could temporarily warm local regions. They could release greenhouse gases that slightly thicken the atmosphere. They could create hydrothermal systems where water and heat interact. Environments that on Earth host thriving ecosystems of thermophilic microbes. But the stagnant lid geology that allowed these volcanoes to grow so large is also part of why Mars became inhospitable. Without plate tectonics to recycle materials and regulate atmospheric composition, Mars couldn't maintain the long-term climate stability that Earth enjoys. It's a trade-off. Mars got the largest volcanoes in the solar system, but it lost the geological dynamism that keeps Earth habitable. Still, Olympus Mons stands, a monument to millions of years of volcanic patience. A mountain so tall it rises above much of Mars' atmosphere. A feature so large it would be visible from space to human eyes if you knew where to look. Frozen in time, dormant probably, but carrying the history of Martian volcanism in its layered flanks, waiting for someone to one day climb it and read its story. Mars experiences perturbed orbital cycles that could have created brief warm periods even in recent geological time. Obliquity, the tilt of a planet's rotation axis, determines how extreme its seasons are. Earth's obliquity is about 23.5 degrees and varies only slightly, between 22.1 and 24.5 degrees, over 41,000-year cycles, stabilized by the moon's gravitational influence. Mars has no large moon to stabilize it. Its obliquity varies chaotically between about 15 and 35 degrees, possibly even more extreme in the distant past, over cycles lasting tens of thousands to millions of years. When Mars' obliquity is low, around 15 degrees, the poles receive less intense summer sunlight. Ice accumulates there, building thick polar caps. The equatorial regions become drier and colder as water migrates poleward and freezes. When Mars's obliquity is high, around 35 degrees, the poles tilt more directly toward the sun during summer. This can cause massive sublimation of polar ice. Water vapor and CO2 release into the atmosphere, temporarily thickening it. Some of this water can migrate toward mid-latitudes, or even the equator, where it falls as snow or frost. At high obliquity, Mars might briefly become more active. Atmospheric pressure increases. Weather patterns intensify. Ice appears in unexpected places. The planet goes through a temporary thaw, not warm by Earth standards, but warmer than its typical frozen state. These cycles are unpredictable on long timescales because Mars' obliquity changes are chaotic. Sensitive to small perturbations from other planets' gravitational influences. But over recent millions of years, models suggest Mars has experienced multiple high obliquity periods, each lasting tens of thousands of years. This means Mars isn't static. It's not permanently frozen in exactly its current state. It cycles through climate states, sometimes colder and more frozen than today, sometimes warmer and more active. If humans colonize Mars, understanding these cycles will be crucial. A colony might experience slowly changing conditions over centuries or millennia. Ice availability might change. Atmospheric pressure might gradually increase or decrease. The climate might shift in ways that require adaptation, but it also means Mars has had recent, geologically speaking, periods that were more habitable than today. If life exists on Mars, it might have survived by adapting to these cycles, thriving during warm periods, forming spores or dormant states during cold periods, waiting underground for conditions to improve again. Mars wobbles, and with each wobble its climate shifts, not dramatically enough to return to the wet warmth of ancient times, but enough to matter. Enough to make Mars a planet that's still changing, still evolving, still full of surprises. The isotope ratios of noble gases in Mars' atmosphere tell the story of how much air was lost to space over billions of years. Isotopes are versions of an element with different numbers of neutrons. They're chemically identical but have different masses. This mass difference matters when gases escape from a planet's atmosphere. When solar wind strips away atmospheric gases, lighter isotopes escape more easily than heavier ones. Over time, this creates a distinctive isotopic signature. The remaining atmosphere becomes enriched in heavier isotopes compared to the original composition. Mars's atmosphere shows exactly this pattern. The ratio of heavier to lighter isotopes of argon, xenon, and krypton is much higher than expected from primordial solar system material. This enrichment tells us that Mars has lost a substantial fraction of its original atmosphere, possibly 90% or more, preferentially losing the lighter isotopes to space. We can even estimate rates of loss. By comparing current atmospheric composition to models of what the original atmosphere should have looked like, and accounting for the isotopic fractionation, scientists can work backwards to estimate how much atmosphere Mars once had and how quickly it was lost. The story isn't pretty. Mars lost most of its atmosphere in the first billion years after its magnetic field shut down. Without magnetic protection, solar wind hit the upper atmosphere directly, ionizing atoms and stripping them away into space. The process continues today, just more slowly. MAVEN has directly measured the ongoing loss, primarily hydrogen, oxygen, carbon, and nitrogen escaping at rates of tens to hundreds of grams per second. Not much on human timescales, but over millions of years, it adds up. This isotopic evidence is like a fingerprint, proof of atmospheric escape that's written into the very atoms remaining. Every xenon atom in Mars' atmosphere carries information about what happened to the atmosphere around it. Every argon atom is a survivor, part of the fraction that didn't escape. The isotopes tell a story of loss, of a planet slowly stripped of its air by solar wind, of an atmosphere thinning over billions of years until only a whisper remains. And they tell us that Mars's transition from habitable to frozen wasn't just about climate change. It was about losing the very air needed to maintain that climate, about becoming unable to hold on to atmosphere, no matter what processes might have tried to replenish it. The noble gases remember. They carry the memory of loss written into their atomic nuclei. And by reading that memory, we understand the tragedy of Mars, a world that couldn't hold on to what it needed most. Mars has strange magnetic anomalies, patches of ancient magnetism frozen into its crust like fossil magnetic fields. These regions are scattered across the surface, especially in the southern highlands. They're not organized into a global pattern like Earth's magnetic field. They're local. Some areas have strong magnetization, others none at all. What they represent is memory. When Mars had a global magnetic field billions of years ago, iron-bearing minerals in rocks aligned with that field as they cooled from molten state. The minerals became permanently magnetized, recording the direction and strength of Mars's ancient field. Then the global magnetic field shut down, but the crustal magnetization remained, frozen in place. These patches of crust remember a time when Mars had magnetic protection, even though that protection is long gone. Some of these magnetic anomalies are incredibly strong, locally stronger than Earth's magnetic field at its surface. If you stood in one of these regions with a compass, the needle wouldn't point to Mars's geographic poles, which have no associated magnetic field, but to the local anomalies' magnetic poles. These anomalies have scientific value. By mapping their strength and direction, scientists can reconstruct what Mars' ancient global field looked like, where the magnetic poles were, how strong the field was, how it changed over time. The anomalies are also evidence for the time scale of Mars' geological evolution. The fact that they're preserved primarily in ancient terrain suggests the magnetic field shut down relatively early in Mars' history, probably within the first 500 million years. Younger volcanic regions don't show strong magnetization because the global field was already gone when those rocks formed. There's something poetic about these magnetic anomalies. They're memories that persist billions of years after the phenomenon they record has ceased. Like fossils, but of a planetary magnetic field rather than of life. They remind us that Mars was once different, protected, shielded by an invisible magnetic bubble that deflected solar wind and preserved atmosphere. That version of Mars is gone, erased by geological time. But these patches of magnetized crust remember. They're witnesses. silent testimony that Mars once had what Earth still has, a protective field generated by a churning metallic core. Evidence that Mars's story could have been different, if only its core had stayed hot, if only its dynamo had kept running. But it didn't. The core cooled. The dynamo stopped. The field collapsed. And only these scattered patches remain, remembering a time when Mars was shielded, protected, perhaps habitable. Some scientists propose that a massive asteroid impact, possibly the one that created the Borealis Basin, may have triggered the shutdown of Mars' magnetic field. This is speculative, but the physics is plausible. Mars's magnetic field was generated by convection in its molten metallic core, hot liquid metal moving in organized patterns, generating electrical currents that produced the magnetic field. A sufficiently large impact could have disrupted this system. The shock wave from a Pluto-sized asteroid striking Mars would have propagated through the entire planet. It might have disrupted the convection patterns in the core, causing the dynamo to fail or become unstable. Alternatively, the impact might have formed a massive upwelling of hot mantle material that altered the heat flow from the core, changing the conditions needed to sustain the dynamo. On Earth, we've never experienced an impact large enough to disrupt core processes. But Mars is smaller, with a proportionally larger impact relative to planetary size. The Borealis Basin impact, if that's what created the northern lowlands, would have been catastrophic, excavating perhaps 40% of the planet's northern hemisphere to depths of several miles. An impact that large would have global consequences. Mega tsunamis if there was an ocean, global seismicity, massive volcanism triggered by pressure release in the mantle, and potentially core disruption. The timing is suggestive. The magnetic field appears to have shut down around 4 billion years ago. The Borealis Basin, if it's an impact feature, formed around the same time. The correlation might be coincidence, or it might be cause and effect. If this hypothesis is correct, then a single event, one catastrophically unlucky collision, changed Mars's entire future. It shut down the magnetic field, which allowed the solar wind to strip away the atmosphere, which caused the climate to deteriorate, which ended Mars' habitability. One impact, one moment of cosmic violence, one asteroid in the wrong place at the wrong time, and Mars never recovered. Earth has been hit by large asteroids, but nothing that fundamentally altered its geology or magnetic field. Mars might not have been so fortunate. It's possible that Mars was simply doomed by its size. Small planets cool faster, and their dynamos eventually shut down regardless of impacts. But it's also possible that Mars might have stayed warm and protected longer, might have maintained habitability longer, if not for that one catastrophic collision. We'll probably never know for certain. The evidence is billions of years old, obscured by subsequent geology. But the possibility remains. Mars might have been struck down just when it was beginning to thrive. Seasonal dark spots appear on Martian sand dunes, called Dalmatian spots because of their appearance, possibly caused by dry ice sublimation, carrying dark material to the surface. These spots appear in late winter and spring on dunes in the southern hemisphere. They start as small dark points, then grow and merge, creating patterns that look organic, almost biological, but are purely physical. Here's the likely process. During winter, carbon dioxide snow covers the dunes. In spring, sunlight penetrates the translucent CO2 ice layer, and warms the dark sand beneath. This causes the ice at the bottom to sublimate, turn directly from solid to gas. The gas is trapped beneath the remaining ice layer. Pressure builds. Eventually, the gas breaks through, geysering out and carrying dark sand particles with it. These particles deposit on the bright ice surface, creating dark fans or spots. As spring progresses, the spots grow, expand, merge. The dunes become decorated with elaborate dark patterns, radial fans, flow-like features, complex branching structures. They look like strange vegetation spreading across the landscape, or like bacterial colonies growing on agar plates. Then, as the CO2 ice completely sublimates and the dunes return to their normal appearance, the spots fade. New bright frost might cover them. Dust might settle. By summer, they've largely disappeared. Next winter, the cycle repeats. The same dunes develop similar patterns, though never exactly identical. The spots are ephemeral art created by physics, erased by seasons, recreated annually. From orbit, these features are beautiful and slightly eerie. They look alive, even though they're not. They remind us how geology can mimic biology, how pattern formation doesn't require life, just the right physical conditions. Early observers of these features considered whether they might actually be biological. Maybe something really does grow on Mars in spring. Maybe microbes or lichens spread across the warming sand. But the physics of CO2 sublimation explains the observations without requiring biology. Still, they're captivating. Every spring, Mars decorates its polar dunes with abstract art. Dark spots and fans and radial patterns that last a few months before fading. A seasonal exhibition, happening whether anyone's watching or not. And if humans ever establish bases near Mars poles, these spots would be an annual event. A reminder that Mars has seasons, cycles, predictable changes, that the planet isn't completely static, that beauty exists even in geological processes. The Dalmatian spots appear. They grow, they merge and fade. And next year, they'll be back, painting the same dunes in slightly different patterns. Mars's way of marking time. The Mars Science Laboratory discovered nitrogen-bearing compounds in Martian rocks, another essential ingredient for life as we know it. Nitrogen is less discussed than water or carbon, but it's equally crucial. On Earth, nitrogen is a component of proteins, nucleic acids, and many other biological molecules. Life requires accessible nitrogen. The problem on Mars is that most nitrogen is locked up in the atmosphere as N2, molecular nitrogen, which is chemically inert and difficult for biological systems to use. On Earth, specialized bacteria can fix nitrogen, convert atmospheric N2 into biologically useful forms like ammonia or nitrates. But this requires sophisticated biochemistry. What Curiosity found were nitrates, nitrogen compounds that are directly biologically accessible. These nitrates were in ancient rocks, formed when Mars had liquid water. The nitrates might have been produced by lightning in Mars' ancient atmosphere, by impacts that provided enough energy to break nitrogen bonds, or by ultraviolet radiation processing atmospheric nitrogen. Regardless of origin, their presence means ancient Mars had usable nitrogen. Not just carbon and water, but the complete set of elements needed for biology. This strengthens the habitability case. If you're trying to determine whether an ancient environment could have supported life, you need to check off items on a list. Liquid water? Yes. Appropriate temperature? Probably. Organic carbon? Yes. energy sources, yes, from sunlight or chemical reactions, and biologically accessible nitrogen, now also yes. The nitrates Curiosity detected are at low concentrations, parts per million, but they're there, preserved in billion-year-old rocks. And if they're in Gale Crater, they're probably elsewhere on Mars too. This doesn't prove life existed, but it removes one potential barrier. Mars had nitrogen that biology could use if biology had arisen to use it. And there's a practical implication. Future Mars agriculture might be able to use indigenous nitrogen sources. Instead of importing all nutrients from Earth, colonists might extract nitrates from Martian soil and use them as fertilizer. It won't be easy, the concentrations are low, but it's possible. Mars had nitrogen. Not abundant, but present. One more piece of the chemical inventory needed for life. One more box checked on the habitability list. Recurring patterns in Martian rocks suggest cyclic environmental changes, possibly driven by astronomical cycles, called Milankovitch cycles. Milankovitch cycles are variations in a planet's orbit and rotation that affect climate. Earth experiences these cycles, changes in orbital eccentricity, axial tilt, and precession that occur over tens of thousands to hundreds of thousands of years. They're responsible for ice ages and warm periods. Mars experiences similar cycles, but more extreme because of its chaotic obliquity variations and lack of a stabilizing large moon. In Gale Crater, the Curiosity rover has examined sedimentary rocks that show distinct layering, alternating between fine-grained mudstones and coarser sandstones. The pattern repeats regularly, suggesting cyclical changes in depositional environment. These layers might record wet-dry cycles, periods when the crater lake was deep and calm, depositing fine muds, periods when it was shallow or dry, with rivers depositing coarser sediments, periods when it filled again, returning to fine deposition. The spacing and thickness of these layers can be measured. If they correspond to known orbital cycles, we can potentially reconstruct ancient Martian climate oscillations, determine how often the lake filled and dried, what drove these changes, how long each phase lasted. It's like reading tree rings, but for an entire planet. Each layer is a time marker. Each boundary between layers represents an environmental shift. Together, they form a record of climate variations, stretching back billions of years. This matters because it shows Mars' climate was never static, even in ancient times. It oscillated, had better and worse periods, experienced cycles of habitability that waxed and waned with astronomical rhythms. If life existed on Mars, it would have needed to adapt to these cycles, survive dry periods, thrive in wet periods, develop strategies for enduring environmental changes that occurred over thousands of years, too slow to notice in a lifetime, but significant over evolutionary time. The rock layers are archives, calendars written in stone, records of a planet that breathed with astronomical rhythms, changing in predictable patterns driven by the gravitational dance of the solar system. And we're learning to read them, layer by layer, pattern by pattern, slowly decoding the climate history of another world. Recent models suggest that sporadic volcanic eruptions might have temporarily thawed parts of Mars even after it became mostly frozen. Mars's transition to a cold desert wasn't necessarily monotonic. It wasn't a smooth decline from warm and wet to cold and dry. There might have been interruptions, brief periods when conditions improved temporarily. Large volcanic eruptions release enormous amounts of heat and gases. On Mars, a major eruption could release greenhouse gases, CO2, sulfur dioxide, water vapor, that temporarily thicken and warm the atmosphere. Create localized hotspots where water ice melts, creating temporary lakes or streams. Generate hydrothermal systems where volcanic heat interacts with subsurface ice, creating warm, wet environments that could last for years or centuries. These wouldn't be global thaws. Mars wouldn't suddenly return to its ancient warm state. But regional, temporary habitable zones might emerge, oases of warmth and water in an otherwise frozen world. If volcanic eruptions happen sporadically throughout Mars' history, and geological evidence suggests they did, then Mars might have experienced recurring brief episodes of habitability long after the main warm period ended. This creates an interesting scenario for potential Martian life. Maybe life emerged during the early warm period, then retreated to refuges as the planet froze. But occasionally, volcanic activity would create new temporary habitats. Life could expand again briefly, then retreat again when conditions deteriorated. A boom and bust cycle of habitability driven by volcanic activity. Not continuous life, but episodic bursts separated by long, cold, dormant periods. This is speculative, but the physics supports it. Volcanism releases energy and materials that can temporarily improve habitability. Mars had volcanism continuing well into its history, possibly as recently as a few million years ago. So these temporary warming events are plausible. It also suggests places to search for life, ancient volcanic regions, especially those with evidence of water interaction. If eruptions created temporary habitable zones, those zones might have preserved evidence, biosignatures, organic molecules, maybe even microfossils. Mars might not have been uniformly frozen for billions of years. It might have had moments, brief flickers, when warmth returned, when ice melted, when chemistry became active again. Volcanic summers on a frozen world, rare, unpredictable, but potentially significant for any life trying to persist through Mars's long freeze. Mars sits near the outer edge of the Sun's habitable zone, that region around a star where liquid water can theoretically exist on a planetary surface. The habitable zone isn't a fixed distance, it's a range, and its boundaries depend on many factors: the star's luminosity, the planet's atmosphere, greenhouse effects, albedo, reflectivity, geological activity. Mars orbits at about 1.5 astronomical units from the Sun, roughly 50% farther than Earth. At this distance, it receives only about 43% as much solar energy per unit area. This places it right at the edge of optimistic habitable zone estimates. With the right conditions, a thick atmosphere, strong greenhouse effect, maybe a darker surface to absorb more sunlight, Mars could potentially support liquid water. It's marginal, but possible. This makes Mars fascinating from an astrobiology perspective. It's a test case for the limits of habitability. How far from a star can a rocky planet be and still develop life? Can marginal cases, worlds at the edge of the habitable zone, host biospheres, or is there a sharp cutoff? Mars suggests that even marginal habitability can work, at least temporarily. The planet did have liquid water for potentially hundreds of millions or even billions of years. It was habitable, despite being at the edge. But it also shows that marginal habitability is fragile. Small changes, losing magnetic field, losing atmosphere, volcanic activity declining, can push a marginal world over the edge into uninhabitability. If Mars had been just a bit closer to the Sun, it might have retained more heat, maintained thicker atmosphere longer, stayed habitable longer. If it had been a bit farther out, it might never have been habitable at all. It's right on the boundary. A world that almost worked, that did work for a while, but couldn't maintain it. This has implications for exoplanet searches. We're discovering rocky planets around other stars, trying to determine which might be habitable. Mars teaches us that location in the habitable zone isn't everything. You also need the right planetary mass, the right geology, the right atmospheric composition, maybe the right moon to stabilize your obliquity. Being in the habitable zone is necessary, but not sufficient. Mars was in the habitable zone and still lost its habitability. Other factors matter just as much. Still, Mars came close, closer than Venus, which is nominally in the habitable zone but became a hellscape, closer than any other world in our solar system except Earth. It's the second best place in the solar system for life, and even though second best means frozen and barren by current standards, it's still close enough that we can imagine transforming it. Close enough that, with technology, we might make it habitable again. A bit farther out, and that wouldn't be true. Mars would be too cold, too distant, too challenging. But at 1.5 AU, it's just barely within reach. A marginal world sitting at the edge of possibility. Of all planets in our solar system, Mars is the most similar to Earth in terms of day length, seasons, geology, and landscape features. Day length, 24 hours 37 minutes versus Earth's 24 hours. Close enough that human circadian rhythms could adapt. Seasons. Both planets have axial tilts that create 4 distinct seasons. Mars's seasons are longer, but the concept is the same. Geology. Both have volcanism, impact craters, erosion features, layered sedimentary rocks. Mars's geology is less active than Earth's, but the fundamental processes are similar. Landscape. Both have mountains, valleys, canyons, polar caps, sand dunes. Mars landscapes look alien but recognizable. You can look at a Mars photo and understand what you're seeing without extensive explanation. Compare this to the alternatives. Venus has a day that lasts 243 Earth days, surface temperatures hot enough to melt lead, and crushing atmospheric pressure. It's less Earth-like than Mars by every measure. Mercury has extreme temperature swings, no atmosphere, and a day-night cycle lasting 176 Earth days. Nothing like Earth. The gas giants don't have surfaces to stand on. Their moons are interesting but fundamentally different. Ice worlds, volcanic moons, nothing terrestrial. Mars wins by default, but it's not just default. Mars genuinely has features that make it feel like a plausible second home. You could stand on Mars and watch a sunset. It would be blue instead of red, but you'd recognize it as a sunset. You could watch clouds drift by, see frost form at night, feel the ground beneath your feet, and know you're standing on solid rock, not ice or exotic materials. The sky has a horizon. Gravity pulls you down, though not as hard. Time passes in day-night cycles that feel natural. Seasons change, even if slowly. This similarity is why Mars captures human imagination more than any other world. It's alien enough to be fascinating, but familiar enough to be comprehensible. We can imagine living there in ways we can't imagine living on Venus or Jupiter or Titan. It's the world we'd choose if we had to leave Earth. Not because it's easy, it's not. Not because it's comfortable, it's hostile. But because it's possible. because we can look at Mars and see not just rock and dust, but potential. A place that could become something more with enough effort, enough technology, enough determination. The most Earth-like planet, which is another way of saying the only other world in the solar system where humans might realistically build a civilization. Terraforming Mars, warming it, thickening its atmosphere, potentially making it habitable for humans without spacesuits, is theoretically possible, but would take centuries or millennia. The basic concept: Mars has resources, water ice in the ground, CO2 frozen at the poles and absorbed in rocks, all the elements needed for atmosphere and hydrosphere. They're just locked up, frozen, unavailable. If we could warm Mars enough to release these resources, feedback loops might kick in. Warming releases CO2, which is a greenhouse gas, which causes more warming, which releases more CO2. Water ice melts, increasing atmospheric pressure and enabling more warming. Eventually, you might reach a tipping point where Mars maintains a thicker atmosphere and warmer temperatures without continuous intervention. Proposed methods include manufacturing greenhouse gases, release perfluorocarbons or other super greenhouse gases into the atmosphere. These could trap heat far more effectively than CO2, jump-starting the warming process. Orbital mirrors. Place enormous mirrors in Mars' orbit to focus additional sunlight onto the surface or polar caps. Increase solar energy input artificially. Asteroid impacts. Redirect ammonia-rich asteroids to impact Mars, both warming the surface and releasing nitrogen and greenhouse gases. Nuclear devices. Detonate fusion bombs above the polar caps to vaporize CO2 ice. Controversial and probably inefficient, but technically possible. Darkening the polar caps. Spread dark dust or microorganisms engineered to darken ice, reducing albedo and increasing heat absorption. Each method has problems: scale, cost, unintended consequences. The fact that we're discussing planetary scale engineering that would take centuries. And there's a fundamental problem. Mars doesn't have enough CO2. Even if we released every molecule of CO2 currently on Mars, in the atmosphere, in the ice caps, absorbed in rocks, we probably wouldn't reach Earth-like atmospheric pressure. We'd get maybe 10 to 20% of Earth's pressure at best. That's not breathable. You'd still need oxygen masks, but it would be enough for liquid water stability, enough for significantly warmer temperatures, enough to make Mars much more hospitable than it currently is. So full terraforming, making Mars a shirt-sleeve environment, might not be achievable with indigenous resources alone. We'd need to import materials, maybe comets, which contain water and volatiles, maybe redirect outer solar system resources over centuries, but partial terraforming, creating a thicker atmosphere, raising temperatures, enabling liquid water, that's within the realm of possibility. Not easy, not quick, but physically possible with sufficient technology and dedication. The ethics are complex. Should we terraform Mars even if we can? What if life exists there now? Do we have the right to transform an entire biosphere? What if we make mistakes and create unintended consequences? These are questions we'll need to answer before attempting any such project. But the physics says it could be done. Mars could be warmed. Its ice could be melted. Its atmosphere could be thickened. It won't happen in our lifetimes. Probably not for centuries. But the possibility exists. Mars could become something different from what it is now, something closer to what it once was, or something entirely new, a hybrid world, partially natural, partially engineered. A second Earth, not identical, never identical, but habitable, breathing, alive in ways it hasn't been for billions of years. One proposed terraforming method involves redirecting ammonia-rich asteroids to impact Mars, releasing greenhouse gases and potentially adding nitrogen to the atmosphere. This sounds like science fiction, and it is for now. But the physics is real. Certain asteroids in the outer solar system contain ammonia, NH3, and other volatile compounds. If you could change their orbits and send them crashing into Mars, the impacts would vaporize the asteroids, releasing ammonia into the atmosphere, provide enormous amounts of heat, warming the surface, potentially release frozen CO2 and water ice from impact sites, add nitrogen from the ammonia to the atmosphere, which is useful for biology and agriculture. Ammonia is a potent greenhouse gas, even more effective than CO2 at trapping heat. Released into Mars' atmosphere, it could jumpstart warming that eventually releases indigenous CO2 and water, creating feedback loops. But the scale required is staggering. You'd need to redirect many large asteroids, objects kilometers across, containing billions of tons of material. Each redirection would require years of spacecraft operations, propulsion systems, precise trajectory calculations, and the impacts themselves would be catastrophic in the short term. Explosions larger than any nuclear weapon, shock waves, dust clouds obscuring sunlight. It would take years or decades after each impact for the dust to settle and the benefits to manifest. You'd probably need to space the impacts out, one every decade or two, allowing the planet to equilibrate between them. A century-long bombardment campaign, carefully orchestrated. The technology required doesn't exist yet. We can barely land small spacecraft on asteroids, let alone push kilometer-sized objects into new orbits. But nothing about this violates physics. It's engineering, not fantasy. There's also risk. What if you miscalculate and send an asteroid on a trajectory that threatens Earth? What if the impacts trigger unintended geological responses, massive volcanic eruptions, crustal fracturing, who knows what? And there's the ethics question again. Bombarding Mars with asteroids is about as unsubtle as planetary engineering gets. Are we okay with that level of intervention? Still, it represents one possible path. Not the only path, maybe not the best path, but a path. A way to add both heat and materials to Mars that the planet currently lacks. Imagine watching from Mars' orbit as an asteroid approaches. A dark speck against stars, growing larger over hours. Then impact, a flash brighter than the sun, a shock wave racing across the surface, a plume of vapor and debris rising into space. The ground trembles, dust spreads, and when it settles, Mars is infinitesimally warmer, its atmosphere infinitesimally thicker. One asteroid among many needed, one step in a process that might take 1,000 years, but a step forward nonetheless. Mars has enough frozen CO2 at its poles that if fully sublimated, it could roughly double the atmospheric pressure, still far too thin for humans to breathe, but a significant step. The seasonal polar caps are mostly CO2 ice, dry ice, several feet thick in winter. Beneath those seasonal caps are permanent deposits of water ice mixed with CO2. And in the polar layered deposits, more CO2 is trapped in the ice layers. If all the CO2 were released into the atmosphere, calculations suggest Mars' atmospheric pressure would increase from about 600 pascals, 0.6% of Earth's, to maybe 1,200 pascals, about 1% of Earth's. That's still incredibly thin, still essentially vacuum by human standards, still requiring spacesuits. But it's a doubling, a significant change that would have climate effects. Higher atmospheric pressure means higher temperatures due to increased greenhouse effect, greater stability for liquid water. The boiling point increases with pressure, stronger winds and more active weather patterns, more protection from radiation, not much, but some. Better aerodynamic efficiency for aircraft and entry vehicles. The question is, how do you release the CO2? The ice is stable under current conditions. It's frozen because Mars is cold. To sublimate it, you need to warm Mars. But to warm Mars, you need more atmosphere. It's a chicken and egg problem. This is why most terraforming proposals involve some external energy input: orbital mirrors, greenhouse gases manufactured and released artificially, asteroid impacts, to kickstart the process. Once you begin warming Mars, the CO2 releases naturally and feedback loops take over. But even if we released all available CO2, we'd be far from Earth-like conditions. We'd need additional nitrogen, oxygen, water vapor, materials that aren't present in sufficient quantities on Mars, at least not in accessible forms. Still, doubling atmospheric pressure is a start. It would transform Mars from extremely thin atmosphere to merely very thin atmosphere. Not breathable, but perhaps thick enough for liquid water to exist stably in certain locations during warm seasons. And liquid water changes everything. It enables chemistry, potentially biology, agriculture in pressurized greenhouses, ice mining operations, all the infrastructure of a permanent human presence. The CO2 is there, frozen and waiting, a resource if we can figure out how to unlock it. Planetary engineering on a scale that staggers imagination, but using materials Mars already has. Not enough to complete terraforming, but enough to begin it. NASA and SpaceX both have stated ambitions to send humans to Mars by the 2030s or 2040s, making the first human landing on Mars potentially less than 2 decades away. This has been the plan before, of course. President Bush announced Mars plans in the 1980s. President Bush Sr. announced Mars plans in 1989. President Obama discussed Mars plans in the 2010s. Each time, the target date slipped into the future as funding, technology, and priorities shifted. But something feels different now. SpaceX is building Starships specifically for Mars missions, a fully reusable rocket system designed to carry 100+ tons to Mars. They're testing it, iterating on it, treating Mars transportation as an engineering problem to solve through rapid prototyping. NASA's Artemis program aims to return humans to the Moon as a stepping stone to Mars. The technologies being developed, life support, habitats, in situ resource utilization, are explicitly designed with Mars in mind. And the technical challenges, while formidable, aren't insurmountable. Propulsion. Chemical rockets can get us there. Transit time is 6 to 9 months each way. Long but manageable. Life support. Recycling air and water for multi-year missions is difficult but achievable. We've done it on the ISS for 20+ years. Radiation. Cosmic rays and solar radiation during transit are concerns. Shielding options include water walls, hydrogen-rich materials, or simply accepting the risk. Entry, descent, landing. Mars' thin atmosphere makes landing large payloads difficult, but we've successfully landed increasingly large robots. Scaling up to human-rated vehicles is the next step. Surface operations, we need habitats, power systems, life support, and resource extraction. All challenging but being actively developed. Psychological factors. years away from Earth, in small crews, with communication delays. Crew selection and support will be critical. The biggest challenge might be political and financial will. A human Mars mission will cost hundreds of billions of dollars. It will require sustained commitment across multiple presidential administrations. It will need international cooperation or massive private investment. But if we manage those challenges, the first footprints on Mars could happen in the 2030s. People alive today, possibly reading this script, might watch live video of humans walking on Mars, picking up rocks, planting flags, establishing humanity's first permanent presence on another planet. It's close enough to plan for, far enough away that much could change, but within the realm of possibility, not fantasy. The first person to walk on Mars has probably already been born. They're somewhere on Earth right now, perhaps training as an astronaut, perhaps still in school, perhaps not even considering space yet. But they're coming, and Mars is waiting. A human mission to Mars would take about 6 to 9 months each way using current propulsion technology, meaning astronauts would spend over a year in space just traveling. 6 to 9 months doesn't sound that long until you think about it. That's spending more time in a cramped spacecraft than most people spend at any single job. That's enough time for babies to be born, for relationships to form and break, for entire chapters of life to unfold. And you can't turn back. Once you launch during a transfer window, you're committed to the trajectory. If something goes wrong, equipment failure, medical emergency, whatever, there's no quick return to Earth. The spacecraft follows orbital mechanics, not human needs. During transit, astronauts would face microgravity for months, causing bone density loss, muscle atrophy, cardiovascular changes. They'd need constant exercise to maintain health, radiation exposure from cosmic rays and solar events, no magnetic field to protect them, only whatever shielding the spacecraft provides, psychological isolation, Earth shrinking to a point of light, communication delays growing from seconds to minutes to 20+ minutes at Mars distance. Real-time conversation becomes impossible. Confinement in a small volume with the same few people for months. Crew compatibility becomes critical. There's nowhere to escape to if tensions rise. Boredom punctuated by maintenance tasks. Most of the journey is waiting, watching instruments, doing exercises, maintaining systems, trying to stay mentally healthy. And this is just the outbound journey. Once at Mars, they'd spend 18 to 20 months on the surface waiting for orbital alignments to make return possible. Then another 6 to 9 months coming home. Total mission duration, 2.5 to 3 years, more than twice as long as any human has spent in space continuously. Longer than many prison sentences, longer than most marriages last before divorce, statistically. This is why Mars missions require extraordinary people, not just technically capable, but psychologically resilient, able to handle isolation, confinement, danger, distance from everything familiar. The journey itself would be an accomplishment, successfully transporting humans across interplanetary space, keeping them alive and healthy for months in the void, would be a triumph of engineering and endurance. And for the astronauts making that journey, watching Earth recede and Mars grow, the experience would be transformative. Months to contemplate where they're going and why. Months to understand the scale of what they're attempting. Months to become truly, existentially aware of the distances between worlds. By the time they arrive at Mars, they'd be different people than when they left. Shaped by the journey, prepared maybe for the even greater challenge of actually living on another planet. Cosmic radiation during the Mars journey and on the surface would expose astronauts to dangerous levels of radiation. A major unsolved challenge for mission planners. Earth's magnetic field deflects most cosmic rays. Our atmosphere absorbs or scatters what gets through. Living on Earth's surface, you receive about 3 millisieverts of radiation per year from natural sources. On the Mars journey, with no magnetic field and minimal shielding, astronauts would receive roughly 300 millisieverts during a 6-month transit. At Mars's surface, with thin atmosphere and no magnetic protection, they'd receive about 200 millisieverts per year, roughly equivalent to getting a full-body CT scan every few days. Total mission radiation dose, 600-900 millisieverts or more, depending on mission duration and solar activity. This significantly increases cancer risk. NASA's career exposure limits for astronauts are designed to keep increased cancer risk below 3% over a lifetime. A Mars mission might approach or exceed those limits in a single mission. And there's acute radiation risk from solar particle events, eruptions from the sun that release intense bursts of radiation. With sufficient warning, astronauts could shelter in a protected area, water tanks, buried habitats. Without warning, exposure could cause radiation sickness or worse. Proposed solutions include spacecraft shielding, water or hydrogen-rich materials surrounding crew compartments, heavy but effective. Faster transit, more powerful propulsion systems to reduce journey time. Nuclear, thermal, or electric propulsion could cut transit to 3 to 4 months. Pharmaceutical countermeasures, drugs that enhance cellular repair or reduce radiation damage, still experimental. Selection criteria: choose older astronauts whose cancer risk is lower, or accept higher risk thresholds. Mars surface protection, underground habitats, lava tubes, or habitats covered with regolith for shielding. None of these solutions are perfect. All involve trade-offs: weight, cost, risk acceptance, ethical considerations about sending people into known danger. The radiation challenge is solvable but not solved. It's one of the major barriers between we could send humans to Mars and we're ready to send humans to Mars. Every day in space is exposure. Every moment on Mars's surface is exposure. Astronauts would accumulate radiation dose constantly, irreversibly, knowing it increases their risk of cancer years or decades later. They'd probably accept that risk. People take risks for exploration, but we owe it to them to minimize it as much as possible. The radiation issue reminds us that space is hostile, that Mars is hostile, that even if we solve propulsion, life support, and landing challenges, the simple fact of leaving Earth's protective bubble means accepting dangers we've never faced before. Growing food on Mars is theoretically possible in greenhouses, but Martian soil contains toxic perchlorates that must be removed before plants can safely grow. Mars has all the elements needed for plant growth: nitrogen in low quantities, phosphorus, potassium, trace minerals. The regolith, soil, has the right particle size distribution and physical properties. With water, nutrients, and controlled environment, plants should grow. The problem is perchlorates, chlorine-based salts that are toxic to plants, and especially to humans, who eat those plants. They interfere with iodine uptake, disrupting thyroid function. They're present across Mars at concentrations of 0.5 to 1% by weight. Removing perchlorates is possible, but requires processing. Washing. Flush soil with water. Perchlorates are highly soluble and will dissolve out. But this requires large amounts of water and creates contaminated wastewater. Bacterial remediation. Certain earth bacteria can break down perchlorates, converting them to chloride and oxygen. Inoculate Martian soil with these bacteria, give them time to work, then plant. Chemical treatment. Use chemical reactions to neutralize perchlorates. Effective but requires reagents imported from Earth or manufactured on Mars. Replacement. Don't use Martian soil at all. Use hydroponics or aeroponics with nutrients synthesized from Martian resources. More complex, but avoid soil contamination issues. Once you solve the perchlorate problem, Martian agriculture faces other challenges. Lower gravity might affect plant growth. We're not sure how. ISS experiments show plants can grow in microgravity, but Mars' partial gravity is unexplored. Lighting. Mars receives only 43% as much sunlight as Earth. Greenhouses would need supplemental lighting or highly reflective interiors to maximize available light. Temperature control. Mars is cold. Greenhouses would need heating during night and in winter, but during day, they might need cooling to prevent overheating. The greenhouse effect works very effectively under low atmospheric pressure. Atmosphere. Plants need CO2, which Mars has plenty of in its atmosphere, but greenhouses would need to be pressurized above ambient Martian pressure, requiring airtight structures. Pollination. No Martian bees. Hand pollination or mechanical systems would be needed for many crops. Despite these challenges, Martian agriculture is feasible. Scientists have successfully grown plants in simulated Martian regolith after removing perchlorates. Potato plants, tomatoes, lettuce, all can grow given the right conditions. For long-term Mars habitation, local food production is essential. You can't ship all food from Earth. Too expensive, too heavy, too slow. A permanent Mars colony needs to feed itself, so greenhouses will be built, carefully sealed, pressurized, temperature-controlled, artificial lighting supplementing dim Martian sunlight, beds of washed and treated regolith, or hydroponic systems, maybe even aquaculture, fish tanks providing protein and fertilizer. Imagine walking through a Martian greenhouse. The air is warm, humid, precious water evaporating from plant leaves, green vegetation, shockingly vibrant against the red world outside. The smell of growing things, of life, in a place where life has never been. It's possible. Difficult, but possible. Mars can feed those who come to live there. The soil just needs preparation. The environment needs control. But the fundamental resources are there. A colony on Mars would have to be almost entirely self-sufficient, with Earth too far away for routine supply missions. The problem is delta V, the change in velocity needed to move between planets. Getting to Mars requires about 9 kilometers of delta V. Getting back to Earth requires similar amounts. Rockets capable of these missions are expensive and can only launch during windows that open every 26 months. This means supply missions from Earth would be infrequent, maybe one every 2 years at best during optimal launch windows. Expensive, hundreds of millions or billions per mission. Slow, 6 to 9 months in transit, during which conditions on Mars might change dramatically. Limited in capacity, even large rockets can only deliver a few tons to Mars. For a colony to survive, it needs to produce locally. Water. Mine ice from subsurface deposits or polar caps. Purify and recycle continuously. Oxygen. extract from water, electrolysis, or directly from CO2 in the atmosphere. Food, grow in greenhouses or controlled environment agriculture. Possibly raise animals if resources allow. Building materials, manufacture bricks, metal, glass from Martian regolith and minerals. Tools and spare parts, 3D printing and manufacturing facilities to make replacement components. Energy, solar panels, possibly nuclear reactors. Energy storage for night and winter. Medicine, synthesize pharmaceuticals from basic chemical feedstocks. Maintain medical equipment. This level of self-sufficiency is unprecedented. Even remote Antarctic research stations rely on regular resupply. Mars colonists wouldn't have that luxury. Any critical component that breaks and can't be manufactured on Mars could threaten the entire colony. A failed water recycling system, a broken oxygen generator, a compromised greenhouse seal. Any of these could be fatal if spare parts aren't available and can't be fabricated locally. This means Mars colonies would need redundancy, multiple backup systems for critical functions, versatile manufacturing, ability to make a wide range of components from available materials, deep knowledge base, colonists skilled in engineering, chemistry, biology, medicine, geology, not specialists, but generalists capable of solving diverse problems. Resource stockpiles, reserves of critical materials, food, water, oxygen, enough to survive equipment failures and wait for repairs. Risk acceptance, understanding that they're living on the edge, that Earth can't rescue them, that survival depends on their own capabilities. It's a fundamentally different model of human settlement than anything in history. Previous colonies, Americas, Australia, Pacific Islands, always had Earth nearby, accessible within months at most. Mars colonies would be truly alone, self-reliant by necessity, not choice. This will shape Mars culture profoundly, a society built on competence, resourcefulness, and mutual dependence, where waste isn't just inefficient, but potentially deadly, where knowledge is survival and ignorance is risk. They'd probably succeed. Humans are adaptable, capable of building sustainable systems even in harsh environments. But it would be hard. Every day would require active maintenance of the systems keeping everyone alive. Living on Mars wouldn't be an adventure vacation. It would be constant work, constant vigilance, constant awareness that you're living in an environment that's actively trying to kill you, held back only by technology and knowledge. But for those who chose that life, it would also be meaningful, purposeful, building something unprecedented, creating human civilization on another world, self-sufficient, independent, truly Martian. Water ice deposits on Mars could provide not just drinking water but also hydrogen fuel for rockets, potentially making Mars a refueling station for missions to the outer solar system. The chemistry is straightforward. Split water, H2O, into hydrogen and oxygen through electrolysis. Hydrogen is excellent rocket fuel. Oxygen is both breathable and an oxidizer needed for combustion. One resource, two critical uses. This transforms Mars from a destination into an infrastructure hub. Instead of carrying all the fuel needed for a return trip from Earth, which dramatically increases launch mass and cost, spacecraft could refuel at Mars. The implications cascade. Earth missions become cheaper, launch with less fuel, refuel at Mars for the return journey. Smaller rockets can accomplish what previously required enormous ones. Mars becomes economically valuable, selling fuel to passing missions. supporting orbital infrastructure, becoming a necessary stop for deep space exploration. Outer solar system access improves. Launching from Mars with its lower gravity and existing fuel infrastructure makes missions to Jupiter, Saturn, and beyond more feasible. The concept is called in situ resource utilization, ISRU, using local resources instead of importing everything. For Mars, ISRU means mining water ice from subsurface deposits, melting and purifying it, electrolyzing it into hydrogen and oxygen, storing these cryogenic fuels until needed, pumping them into spacecraft for launches. The technology exists. We know how to mine ice, purify water, perform electrolysis, and store cryogenic fuels. It's all established technology, just not yet deployed on Mars. The challenge is scale and reliability. You need large-scale operations, processing tons of ice, generating megawatts of power for electrolysis, maintaining cryogenic storage for months or years. And it all needs to work in Martian conditions: cold, dusty, low pressure, high radiation. But if achieved, Mars becomes more than a destination. It becomes a stepping stone, a gas station in space, a place where missions stop not just to explore Mars, but to prepare for what lies beyond. Imagine spacecraft arriving at Mars orbit, not landing, just rendezvousing with a fuel depot. Tankers launched from Mars' surface carry liquid hydrogen and oxygen. The spacecraft refuels, perhaps transfers crew or cargo, then continues outward to the asteroid belt, to Jupiter's moons, to Saturn's rings. Mars becomes the gateway to the outer solar system, not because of its location, though that helps, but because it has resources accessible enough to exploit with reasonable technology. Water ice, abundant, accessible, useful, not just for Martian colonists, but for all future space exploration. The first water mining operations on Mars might be small, supporting local needs, proving the technology. But eventually, they could grow into an industry: fuel production, export, making Mars not just self-sufficient, but economically relevant to the broader solar system. From dead desert to economic hub, from endpoint to waypoint. All because of frozen water waiting beneath the dust. Some scientists suggest that life on Earth might have originally come from Mars, carried here on meteorites billions of years ago, a hypothesis called panspermia. Here's the logic. Life on Earth appeared relatively quickly after the planet cooled enough to support it, within a few 100 million years. Either life emerges very easily from chemistry, or it was seeded from elsewhere. Mars was potentially habitable earlier than Earth. It cooled faster due to smaller size. It may have had liquid water and clement conditions, while Earth was still being bombarded by massive impacts that periodically sterilized the surface. Mars gets hit by asteroids. These impacts can launch rocks into space. We know this because we found Martian meteorites on Earth. If rocks can make the journey, so can any microbes embedded in those rocks. Space is cold, but it's also an excellent preservative. Microbes could survive in dormancy for millions of years during the transit. When they finally impact Earth, some might survive the entry and landing, finding themselves in a new habitable environment. If this happened, we might all be Martians. Descendants of microbes that evolved on Mars, got blasted into space, hitchhiked to Earth on rocks, and then evolved here into all the diversity of terrestrial life. It sounds like science fiction, but it's physically plausible. We know life can survive extreme conditions. Some microbes endure radiation, vacuum, temperature extremes that would destroy most organisms. Rocks regularly travel from Mars to Earth. We have hundreds of samples. Early Mars might have been more habitable than early Earth during certain periods. Life on Earth appeared quickly once conditions allowed, suggesting it didn't need to originate here, just arrive. The hypothesis is testable. If we find life on Mars, and if it uses the same genetic code, same chirality of molecules, same fundamental biochemistry as Earth life, that would suggest a common origin. Either panspermia from Mars to Earth, or from Earth to Mars, or both seeded from elsewhere. If Martian life is fundamentally different genetic code, different molecular building blocks, different chemistry, that would suggest independent origins, which would be even more profound. It would mean life can arise through multiple distinct pathways. But if panspermia is true, it means life might be more widely distributed than we think, seeded between planets by natural processes. Earth and Mars share biological history. We're not separate biospheres, but connected ones. The origin of life question becomes more complex. Where did life first arise? Mars? Earth? Somewhere else entirely? We're potentially studying our ancestors when we search for Martian fossils. It also means we need to be careful. If life can travel from Mars to Earth naturally, it can travel from Earth to Mars on our spacecraft. Contamination isn't just a scientific problem. It's potentially reseeding Mars with terrestrial life billions of years after it might have first arrived. We might not be discovering Martian life. We might be rediscovering our own origins, carried on rocks across interplanetary space, connecting worlds in ways we're only beginning to understand. We still don't know exactly why Mars lost its magnetic field. Theories include massive impacts, core cooling, or both. But definitive evidence remains elusive. Magnetic fields in planets are generated by dynamo action, convection of electrically conductive fluids in the core creating electrical currents that generate magnetic fields. For Mars, this would require a liquid metallic core, sufficient heat to drive convection, rotation to organize the convection patterns through Coriolis effects. Early Mars had all three. We know it had a magnetic field because crustal magnetization is preserved in ancient rocks. But around 4 billion years ago, the field shut down. The dynamo stopped. Why? Cooling hypothesis. Mars is small. Small bodies cool faster. They have higher surface area to volume ratios, meaning heat escapes more efficiently. Mars' core might have simply cooled to the point where convection stopped. No convection, no dynamo, no magnetic field. This seems inevitable for Mars eventually. But did it happen as quickly as observed? Models suggest Mars' core should have stayed hot longer. Something might have accelerated the cooling. Impact hypothesis. The giant impact that possibly created the Borealis Basin might have disrupted core convection. The shockwave could have disturbed the organized flow patterns needed for dynamo action. Or the impact could have created a massive mantle upwelling that altered heat flow from the core. This is speculative. We don't have direct evidence that an impact caused dynamo failure, but the timing is suggestive. Mantle overturn. Chemical changes in Mars' mantle might have altered convection patterns, shutting down the dynamo. This is even more speculative, but possible. The truth might be a combination. Maybe Mars' core was slowly cooling and losing dynamo efficiency. Then an impact delivered the final disruption that pushed it over the edge. The field, weakened, flickered, and died. Whatever the cause, the consequences were catastrophic. Without magnetic protection, solar wind stripped away atmosphere. Radiation levels at the surface increased. Climate destabilized as atmospheric pressure dropped. Water could no longer remain liquid on the surface. Mars transformed from potentially habitable to frozen desert. One event or process, the loss of the magnetic field, changed everything. It's arguably the most important event in Martian history after the planet's formation. Understanding why it happened matters because it tells us about Mars' interior structure and thermal evolution. It might explain whether Earth's magnetic field is permanent or could eventually fail. It informs our understanding of exoplanets, how many rocky planets maintain magnetic fields long term. But 4 billion years later, the evidence is obscured. The rocks that might definitively answer the question have been eroded, buried, or altered. The core itself is inaccessible. We can study it only indirectly through seismology and gravity measurements. Mars keeps this secret well. We know the magnetic field died. We know approximately when. But the why remains uncertain, hidden in the planet's cold, quiet interior. The question of whether life ever existed on Mars remains one of the most profound, unanswered questions in science. The answer would fundamentally change our understanding of life's place in the universe. If life exists or existed on Mars, it means life arises relatively easily. 2 planets in the same solar system, both developing life, suggests it's not a rare accident, but a probable outcome given the right conditions. The universe is probably full of life. If 2 out of 8 planets in our system host or hosted life, extrapolate to billions of planets around billions of stars, life might be common, even ubiquitous. We need to search harder. If life arose on Mars independently from Earth, it means multiple origin events, suggesting biology emerges wherever chemistry permits. If life never existed on Mars despite ancient habitable conditions, it means life is rare. Even with water, nutrients, energy sources, and time, life doesn't necessarily emerge. Perhaps the chemical steps are improbable. Perhaps specific conditions we don't understand are required. Earth is special. We might need to revise our estimates of how many exoplanets are truly habitable. Having water and moderate temperatures might not be enough. The Fermi paradox deepens. If life is so rare that even Mars never developed it, that helps explain why we haven't detected alien civilizations. Intelligence might be vanishingly rare in the universe. We don't know yet. The Viking experiments were ambiguous. Curiosity has found organic molecules, but can't determine their origin. Perseverance is collecting samples, but we won't analyze them definitively until they're returned to Earth, and that mission is years or decades away. The question haunts Mars. Exploration. Every rock analyzed, every sample collected, every image examined, all are searched for that one unambiguous sign, a fossil, a distinctive isotopic signature, a pattern of molecules that can't be explained by chemistry alone. So far, nothing definitive. Tantalizing hints, promising environments, but no smoking gun. Maybe we're looking in the wrong places. Maybe Martian life existed, but left no fossils, ephemeral, small, failing to mineralize in ways we'd recognize. Maybe it's still there, hiding underground where we haven't reached, dormant in subsurface ice, clinging to existence in protected refuges. Or maybe it never existed. Maybe Mars came close but didn't quite cross the threshold from chemistry to biology. Maybe we're alone, at least in the solar system. The answer matters profoundly, not just scientifically, but philosophically. Are we a cosmic accident, alone in a vast universe? Or are we one example among countless others, a single voice in a chorus of life? Mars might tell us, if we keep searching, if we're patient, if we're willing to accept whatever answer we find. Ancient Mars may have been habitable for 1 billion years, long enough for complex life to evolve if it followed Earth's timeline. On Earth, life appeared roughly 3.8 to 4 billion years ago, very quickly after the planet became habitable. But complex multicellular life didn't emerge until about 600–800 million years ago. Simple microbial life dominated Earth for over 3 billion years before evolution produced anything more sophisticated. If Mars had 1 billion years of habitability from roughly 4 billion to 3 billion years ago, that's time enough for life to emerge from chemistry, evolution to explore simple microbial forms, possibly the development of photosynthesis or other metabolic strategies, the formation of microbial mats, stromatolites, or other colonial structures, but probably not complex multicellular life, not animals or plants. 1 billion years might not be enough for that, based on Earth's timeline. So if life existed on Mars during its habitable period, we should expect it to be simple, microbial, bacterial, or archaeal in complexity, maybe with interesting metabolisms adapted to Martian conditions, but not complex. This matters for what we search for. We're not looking for Martian fossils resembling shells or bones. We're looking for microscopic structures, chemical signatures of metabolic activity, isotopic ratios that suggest biological fractionation, patterns in rock layers that indicate microbial mats. 1 billion years is actually quite long. Earth's entire Phanerozoic eon, the time of complex visible life, is only about 540 million years. The dinosaurs ruled for about 160 million years. Human civilization is about 10,000 years old, so 1 billion years of Martian habitability is a substantial period, long enough for life to emerge, diversify, adapt, maybe even approach the complexity that microbial life on Earth achieved before multicellularity. But then it ended. The climate shifted, water disappeared, temperatures plummeted. If life existed, it either went extinct entirely, leaving only fossils and chemical traces, adapted and retreated to refuges, underground, in ice, wherever conditions remained marginally tolerable, entered dormancy, waiting for conditions to improve. We're looking at the ruins of a potentially habitable world, a biosphere that flourished for 1 billion years and then vanished, or nearly so. If we find evidence of that biosphere, it would be like discovering Pompeii, a snapshot of life frozen in time, preserved in the moment of Mars' climate catastrophe. 1 billion years, long enough for evolution to do interesting things. Not long enough to create complexity, probably, but long enough that if life was there, it should have left marks we can find. If microbial life exists on Mars today, it's probably deep underground where liquid water can still exist and radiation can't penetrate. The surface is hostile. Intense UV radiation, oxidizing chemicals in the soil, extreme temperature swings, no liquid water. Any surface life would need to be extraordinarily hardy. And even then, it's not clear how metabolism could function under those conditions. But underground is different. Temperature stabilizes. Geothermal heat from Mars' interior provides warmth, even if slight. Radiation is blocked by meters of rock, and crucially, liquid water might exist, not in lakes or rivers, but in thin films on mineral grains, in microscopic pores, in brines kept liquid by dissolved salts and pressure. Enough water for chemistry, possibly for biology. On Earth, we find life everywhere. There's liquid water, including deep underground, microbes in aquifers kilometers below the surface, in rock fractures, in ancient isolated water pockets. They metabolize slowly, reproduce rarely, existing in near dormancy, but they're alive. Mars might have similar ecosystems, deep subsurface environments where microbial communities persist, isolated from the surface, living on chemical energy from water-rock interactions. These communities would be slow-growing. Metabolism would be minimal in the cold, low-nutrient conditions, sparse, low population densities spread through rock fractures and pores, isolated, possibly existing in disconnected pockets, each evolving independently for millions of years. Ancient, potentially descended from surface life that retreated underground as Mars froze. Finding them would be extraordinarily difficult. We'd need to drill, possibly kilometers deep. We'd need to sample carefully, avoiding contamination. We'd need to culture or analyze samples using techniques sensitive enough to detect sparse, slow-growing organisms. No current mission can do this. Our rovers scratch the surface, drill a few inches or feet at most. The deep subsurface is unexplored, inaccessible with current technology. But it's probably the most likely place for extant Martian life. If such life exists, protected, stable, wet enough, a refuge where biology might have survived Mars's long freeze. If we ever send drilling missions, perhaps to polar regions where ice is closer to the surface or to geothermal hotspots, we might find it, not in abundance, not thriving, but existing, persisting, waiting, life clinging to Mars' deep interior, the last survivors of a biosphere that once covered the planet. Or perhaps life that evolved underground, never experiencing the surface, adapted to darkness and isolation from the beginning. Either way, if it's there, it's hiding, deep beneath the dust and rock, in the one place on Mars where the planet still resembles its ancient self, just slightly. Mars has been dead or dormant for over 3 billion years, yet it still captures our imagination like no other planet. Perhaps because in Mars we see both Earth's past and its possible future. Early Mars resembled young Earth. Both had water, dense atmospheres, volcanism. Both were dynamic, geologically active worlds with the ingredients for life. Earth stayed habitable. Mars didn't. Why? Size, primarily. Mass. Mars cooled faster, lost its magnetic field sooner, couldn't maintain its atmosphere. Through no fault of its own, just the physics of being a smaller world. Earth might face the same fate, eventually. Our planet is cooling too, just much slower. In a few billion years, Earth's core might freeze. The magnetic field might shut down. Plate tectonics might cease. The very processes that keep Earth habitable could gradually fail. Mars shows us what that looks like. A dead world that once lived. A planet that had everything needed for habitability and lost it. A cautionary tale about planetary mortality. But Mars also shows resilience. Even frozen and airless, it hasn't vanished. It hasn't been completely eroded away. The geology remains, preserving evidence of its past. The water is still there, locked in ice. The resources exist for potential transformation. Mars is dead, but not erased. Dormant, but not destroyed. And that gives hope. Maybe Mars can be revived, at least partially. Maybe Earth's future, if it parallels Mars, isn't permanent death but just dormancy, a state that could, with sufficient effort, be reversed. We study Mars partly to understand planetary science, but partly to understand ourselves, to see what happens when a habitable world loses its habitability, to learn what conditions are necessary and sufficient for long-term planetary health, and maybe to practice. Because if we can learn to sustain life on Mars, a hostile, frozen desert, then we'll know we can sustain life on Earth even as conditions change. Mars is both warning and practice ground, both graveyard and construction site, both past and future. A world that died so we could learn from its death. A world that waits, patient, for someone to attempt its resurrection, or at least to understand why resurrection matters. Every grain of Martian soil tells a story, spanning billions of years, from volcanic eruptions to water flows to cosmic bombardment. Pick up a handful of Martian dust and you're holding particles of volcanic rock from eruptions that happened when dinosaurs ruled Earth, or long before Earth had dinosaurs. Iron oxide that formed as water slowly oxidized rock over millions of years. Impact debris from asteroid collisions that cratered the surface. Possibly organic molecules delivered by meteorites from the outer solar system. Minerals that crystallized in ancient lakes under skies that may have held rain. Dust that's been lofted by winds, settled, and lofted again for eons, traveling miles or continents through Martian atmosphere. Each grain has a history. Each one has been somewhere, done something, witnessed events that no longer occur. The dust is an archive, mixed, churned, distributed by wind, but preserving information in its chemical and mineralogical composition. This is why Mars exploration involves so much grinding, drilling, and chemical analysis. We're not just identifying minerals, we're reading the stories encoded in them. A particle of olivine formed in Mars' mantle, brought to the surface by volcanism, weathered by ancient water. A grain containing carbonates, water and CO2 interacted here under conditions we're trying to reconstruct. A sulfate crystal formed in evaporating acidic water, possibly a late-stage feature after most of Mars' water was gone. The dust devils that dance across Mars aren't just wind phenomena. They're mixing stories, churning history, taking particles from ancient terrain and depositing them on younger surfaces, homogenizing billions of years of geological record into a fine, wind-blown mixture. And when we drive rovers through this dust, we're literally driving through time. Every meter traveled crosses geological eras. Every drill sample extracts a moment from Mars' past. The entire planet is a museum without walls. Every rock, every pebble, every dust grain is an exhibit. Some we can read with current instruments. Others will remain mysterious until we develop new techniques or return samples to Earth. But the stories are there, written in atoms and minerals, in crystal structures and isotope ratios, in the way particles stick together or scatter in wind. Mars remembers everything, not in books or recordings, but in matter itself, in the very substance of the planet, and we're learning to read it, slowly, grain by grain, building a narrative of a world that was young when Earth was young, that grew old while Earth stayed vital, that waits now in frozen silence, its stories waiting to be told. Looking at Mars today is like looking back in time at what early Earth might have resembled before life transformed it. Mars is a mirror showing us our planet's childhood, preserved in rusty stillness. Early Earth, 4 billion years ago, probably looked somewhat Martian, volcanic, cratered, thin atmosphere, slowly thickening, water beginning to accumulate, no oxygen in the air that came later, produced by life. Then Earth diverged. Life emerged and eventually transformed the atmosphere, filling it with oxygen. Plate tectonics continued, recycling crust and regulating climate. The magnetic field persisted, protecting atmosphere from stripping. Earth stayed dynamic. Mars froze in an earlier state. Not exactly like early Earth, every planet is unique, but closer to that primordial condition than Earth's current state. When we study Mars, we're studying what Earth might have become if certain conditions had differed. If Earth had been smaller, if life hadn't emerged, or had emerged but remained simple and sparse, if geological activity had shut down early. This makes Mars scientifically invaluable. It's a preserved example of planetary evolution that took a different path. A controlled experiment, in a sense. Same starting conditions, different outcomes, but it's also humbling. Earth's habitability isn't guaranteed or permanent. It's maintained by a complex interplay of size, composition, orbital position, magnetic field, life itself. Change any of these factors, and Earth could become Mars-like. Mars shows us that habitability is fragile, that planets can die, that the conditions we take for granted, breathable air, liquid water, protective magnetic fields, are not universal or eternal. It also shows us that dead doesn't mean erased. Mars preserves its past. The ancient riverbeds remain, the minerals remember water, the geology tells stories. A planet can lose its habitability but keep its history. And maybe, just maybe, it shows us that dead doesn't have to be final, that with enough knowledge and technology, a planet's trajectory can be altered, that Mars could potentially be warmed again, thickened atmospherically, partially restored, not to exactly what it was, that's probably impossible, but to something new, something hybrid between natural Mars and engineered Mars. A second chance at habitability, this time aided by intelligence instead of just natural processes. Mars is our mirror. It reflects what we were, what we could become, and possibly what we might create. A dusty mirror, cracked and ancient, but a mirror nonetheless, showing us ourselves across time and possibility. The red dot in our night sky represents humanity's greatest off-world hope, a destination, a mystery, and perhaps one day, a home. For thousands of years, humans looked at Mars and wondered. We named it after gods, drew maps of imaginary canals, wrote stories about Martian civilizations, always wondering, always imagining. Now finally, we're going there. Not just robots, though they've been extraordinary pioneers, but humans, within decades probably, within your lifetime, possibly. Mars represents something profound in human consciousness. It's the next place, the world beyond Earth that's most within reach, the destination that combines challenge with possibility. It's not the moon, too close, too barren, too obviously just an extension of Earth. It's not Venus, too hostile. It's not the gas giants, too alien, no surface to stand on. It's not the outer solar system, too distant, too cold. It's Mars, just far enough to be an achievement, just hospitable enough to be survivable, just mysterious enough to be worth exploring. And as you drift towards sleep tonight, imagine this. Somewhere on Mars, in a valley that held water billions of years ago, future humans will stand. They'll watch Earth rise in the evening sky, a blue star, distant but visible. They'll remember humanity's origin, but they'll be building something new, They'll grow food in greenhouses, extract water from ice, manufacture building materials from dust. They'll raise children who know Martian sunsets as home. They'll establish the first human society on another world. And those children, and their children, will look up at Earth the way we look up at Mars, that distant blue world where humanity began. Interesting, historic, but not home. Home will be Mars, red dust under their boots, thin air requiring pressurized habitats, low gravity making them taller, bouncier, different from Earth humans. A cold world requiring constant technological life support, but home nonetheless. Mars waits for them, for us, for whoever takes that first step onto rusty soil and says, "Here, we're staying here. This is ours now too." The red dot that watched our ancestors, that sparked our curiosity and fueled our dreams, that represents both our past, the explorer spirit that drove us across Earth, and our future as a multiplanetary species. Mars, destination, mystery, challenge, hope, and perhaps one day, home. We've traveled far tonight. 100 facts about Mars, 100 glimpses of a world that's frozen, dusty, ancient, and yet somehow full of possibility. Maybe you're still awake, mind buzzing with images of blue sunsets and giant volcanoes. Or maybe you've already drifted off, these words becoming part of your dreams, mixing with your own thoughts about red planets and distant futures. Either is fine. That's what these journeys are for, to give your mind something to hold on to as you slip away from wakefulness. Something larger than daily concerns, something that reminds you how vast the universe is, how much we've learned, how much more we have yet to discover. Mars isn't just a planet. It's a question we're still answering. It's a story we're still reading, written in rocks billions of years old. And somewhere in that story might be answers to the deepest questions we ask. Are we alone? How did life begin? What happens when planets die? Can we save worlds or create new ones? Mars might tell us, if we keep asking, if we keep exploring, if we keep looking up at that red dot and wondering what it has to teach us. Sleep well. Dream of red deserts under butterscotch skies, of ancient rivers that flowed when Earth was young, of humans yet to be born, taking their first steps, rusty soil. Mars is waiting, patient, quiet, red. And tomorrow, when you wake, it'll still be there. A dot in the sky, a world of mysteries, a reminder that the universe is vast and we're just beginning to explore it. Good night.